And for this, let me congratulate to Department of Mechanical Engineering and Department of Information Technology, the heads, Dr. Yadav and Dr. Savji. The organizing team, Dr. Satish More, Dr. Davas, Dr. Biradar, for taking enormous efforts for making this program successful. And on behalf of the Nutan Maharashtra Institute of Engineering and Technology, we are very thankful to AICTE for sponsoring this FDP and hosting and giving us an opportunity for organizing this faculty development program at NMIET Talegaon, Pune. Dear friends, as a time when the world is transitioning towards sustainable growth, the need of clean energy, intelligent technologies, smart systems, and climate change solutions has never been more urgent. So across the globe, countries are accelerating the adoptable of renewable energy systems, solar systems, wind energy, biomass, then other green technologies to reduce the carbon emissions and secure a sustainable future. So parallel to this, we have smart systems powered by digital technologies, artificial intelligence, and intelligent control mechanism are reshaping the way we generate, distribute, and consume energy. So I think this is very relevant theme for all of us. If you go and see the new national education policy, wherein we are going to implement the holistic and multidisciplinary curriculum framework for the students. And I think these topics like smart systems, climate change, and renewable energy, these are the interdisciplinary topics are rightly chosen during this faculty development program. So climate change remains one of the greatest challenge for us. Its impact on ecosystems, weather patterns, agriculture, infrastructure, and human life is undeniable. So as an educator and researcher, it is our responsibility to equip ourselves with this knowledge, tools, skills necessary to contribute meaningful to sustainability, innovation, and policy development. So now we are integrating all such type of topics in our curriculum framework to strengthen our academic excellence and also to strengthen the research culture at the institute. Dear participants, let me tell you that this institute is part of Nutan Maharashtra Vidya Prasarak Mandal. So this Nutan Maharashtra Vidya Prasarak Mandal is established since more than 100 years. The great freedom fighter Lokmanya Bal Gangadhar Tilak was the founder member and the chairman of governing council of this trust. And institute, that is NMIET, is committed for quality education. As Government of India is transforming education, so we are committed to that, and we have adopted that transforming systems at our institute. I think this is one of the very good initiative taken by our departments, that is faculty development program on renewable energy, smart systems, and climate change. So this FDP has been thoughtful design to bring the gap between emerging technologies and academic practices. So over the next few days, this is not just one session. If you go and check, there are many resource persons from various organizations like NITs and IITs and industry. They are going to deliver the sessions for all the participants. So participants will gain insights from distinguished experts who will share their expertise on renewable energy systems, smart grid technologies like smart power grid, climate change modeling, and sustainable development strategies. I'm confident that the sessions and discussions and hands-on activities will not only enrich your technical understanding, but also inspire new research ideas, collaborative projects, and innovative teaching methodology that we are going to discuss during this faculty development program. And I hope that your active participation will be highly appreciated during this FDP. So I would like to extend my appreciation to the organizing team for their dedication efforts in planning this program, and to all the resource persons for kindly agreeing to share their knowledge with us. I also thank all the participating faculty members for their enthusiasm and commitment to continual professional development. So, dear friends, I wish you all the best to gain all the knowledge, and I hope that you will also discuss some of the innovative ideas in your mind during this faculty development program. So thank you very much for giving me an opportunity to interact with all the participants. Thank you once again.
Thank you, sir. It is really a cup of coffee to energize our strength in this evening. Once again, I would like to thank our director, Dr. Pramod Patil, sir. Now it's time to introduce, welcome to our one more great personality, Rajesh Ji Maske, sir. Sir is about, if I want to tell about sir, it will take a more time. So in short, I will give his introduction. Sir is a first generation entrepreneur, and he is heading as a managing director of the Mass Polymer Mass Group of Company. He is also director of the several other companies and LLPs within this group, like Mass Polymer Private Limited, which has started in 1999, Mass Polymer Insulators Private Limited, INSIT Mass Transmissions Private Limited, Manas Automotive Systems Limited, Mass Staples LLP, and also sir is heading as a director in the regard of his vision and the mission of promoting the entrepreneurship ecosystem among the young students. He formed a company that is NIC, that is a Nutan Incubation Center, which is formed in 2023, where he served as a director of this foundation. Along with this, he has over a 2 decade of experience in the rubber products and automotive components industry. So this extensive experience has been a key factor in establishing the long-term relationship with the major customers. He is particularly recognized for his leadership in the mass polymers. About the mass polymer, earlier this system as a mass polymer, which began in the journey in the 1997 as a mass seals cooperative limited, which was manufacturing the PTFE, that is the polytetra fluoroethanol seals. Later, under the leadership of the Maske sir, the company was officially changed as a Mass Polymer Private Limited in 2001. So this marked as a significant step in its formal establishment and the growth. Sir is also associated with the different companies, and he holds different directorships. He is mainly based on the Talegaon, Dabade, where the mass polymer is also located in the Talegaon, which has given the more employability to the near around the students who are looking for their jobs. Rajesh Maske sir is also involved in a social activities through his association with the educational and the community organization. He is also visiting the different, even the College of Ayurveda and the Research Center, Pune, and he has given the or delivered the lectures on the topic of the National Girl Child Day as well as the National Voters Day to the student. So, sir is one of the visionary leaders, which we all are fortunate to have the sir. Currently, sir is heading as a treasurer in the Nutan Maharashtra Vidya Prasarat Mandal, Talegaon Dabade, and also sir is serving as a chairman to the Institute Nutan Maharashtra Institute of Engineering and Technology. Sir, we welcome you for this ATAL FDP. Just a minute. Sir, I think sir is
So
sir
because
has left the meeting.
I have a problem, I think sir is not available online. So we will move ahead. Whenever the sir is available online, we will interact with sir.
Yes, sir. Sure, sir. Thank you, sir. Okay. Now we are moving towards to the keynote speaker and the today's chief guest. So today's chief guest is Dr. Ajay Chandak, sir. Sir, it is my privilege to introduce you, as well as sir is one of the speaker to this ATAL FDP. Dr. Ajay Chandak, he is a distinguished renewable energy technologist, innovator, and the educator with the 3 decades of the impactful contribution to the field of solar energy, sustainability, and the clean cooking technology. Dr. Chandak holds the PhD in the mechanical and specifically in the solar energy from DAVV. He has graduated MTech from the IIT Bombay and BE in mechanical engineering from the COEP Pune. He is also chartered engineer and the certified energy auditor, BAA and the Government of India, credential that underline his technical excellence and the leadership in the energy sector. He currently serves as the managing director of the Chandak Innovations LLP and proprietor of the Sustainable Innovations organizations deeply involved in these 2 organizations deeply involved in the R&D technology, which includes all the TRL levels, that is the technology transfer and the entrepreneurship mentoring within the renewable energy ecosystem. Dr. Chandak has the exceptional record of the developing and commercializing more than 10 renewable energy technologies, backed by 20 patents, many of which have successfully reached industry as well as the market and towards to the society. His consultancy footprint spans reputed national and international organizations, including United States, MNRE, even GERMI, Oxford University, UK, and the TIWS. He has played a vital role in the advancement of solar concentrator technology and the engineering in the collaboration with the ATE, then DST, and the contributing a global technology as an export. Dr. Chandak has conducted more than 20 plus international training programs for the research scholars and the FDP with the faculty development program, including EU-funded initiatives in Africa, and he has delivered more than 100 plus expert lectures at a premier institute such as IITs, TIFR, NITs, ASCI, ESCI, and all. Also, he has delivered the lectures in the Portugal, Africa, as well as the Germany. His remarkable work has earned him a numerous prestigious awards, including the National Grand Challenge Award from the DST, Wintex Gold Prize Indonesia, SCI Order of Excellence from USA, and multiple awards from the government of Maharashtra. He is also honored as a COEP Abhiman Award in 2019. Beyond his technical achievement, he has held the influence in positions such as the board member of ISTS, Global Advisory to Solar Cookers International USA, Technology Agent at DST, and expert member of BIS. He has contributing to the development of an Indian standard for this solar concentrator. He is also the founder and the chairperson of PRINCE, a network dedicated to clean energy innovation. Sir, as if I go with all the CV, it will take a more time. So with this introduction, sir, it is our honor to you have in our FDP as a keynote speaker. We are welcoming you for this ATAL FDP, sir.
Hello,
Sir, am I
everyone.
audible?
Yes, sir, audible.
Yes. Maurice sir, you can stop sharing so that sir can share his PPTs.
Just a minute, it's just small glitches with the sharing.
Sure.
I should be sharing the entire screen, I think. Or
Entire
the-
screen.
Yes, sir.
I think something wrong. I need to.
No, sir, it is visible. It is
It is
visible to
visible,
us.
sir.
Uh,
Just
but I can see only the presentation and not the people. I don't know.
Okay, okay.
But is this okay?
Yes, sir.
yes,
Yes.
sir. Yes, sir.
You
Yes,
can
sir.
see the slide transition.
Yes, sir.
Yes, sir. Absolutely fine, sir.
Okay, I can't see the people, but fine. As long as I see the presentation, it's okay. So, hello everyone.
Hello, sir.
Okay, there is a lot of noise. Okay. Hello everyone. Welcome to this important session. One of the advantages that I normally see with these kind of lectures is I can see a lot of my colleagues, some students, and some other people that I know well because of this work in renewable energy. So we get a chance to interact. I just saw name of Professor Bhale here. I just met him 1 week ago, last Monday we met. And thanks to the institute for choosing right topics. Last time I think it was industry 4.0, but from the energy aspect, and now it's about solar energy sustainability and climate change. I have spent 31 years in academics, so it's almost now how much? 8 years. I left my academic career to pursue my passion in innovation and R&D. And my academic career was also a bit different than a very typical professor in engineering. I had a lot of professional and R&D activities ongoing simultaneously. And fortunately, I had opportunities to work with some of the best universities in the world. Most of them were after I left my academic career, but we had some serious R&D work with UIUC USA, University of Illinois, Urbana-Champaign, and then Oxford University, UK. And while working with these institutes, I realized some lacunas that our education systems have. especially why we are working with Oxford University for more than now 6 years. And in money term also, I think the transaction more than 1.5 crore rupees. And we realized how these so-called very reputed universities work and our system, how they work. In engineering stream, most of these universities, they have an aptitude of commercializing their research or their innovations in whatever way possible. Like Oxford University has its own company, and that company name is Oxford University Innovations Limited, and that is a fully owned subsidiary of the Oxford University. So all the research that happens there, the innovations, the startups, they call in UK spin-offs, all of them are handled by this company. So the academic staff, the professors, they are left to primarily the academic and the research work, but this company takes on its head the responsibility of filing patents, getting research grants, selling research, and licensing patents, starting startups or the spin-offs they call. And it's not a small company. Like in 2018, when I first interacted, the turnover of this company was 200 million pounds, so around 2,000 crore rupees in today's terms. So that's the company that handles the commercial part of it. Now in India, we do some research, not much, but most of our research dies down in research papers or the PhD thesis or even patents. Lot of people file patents, but how many them monetize or commercialize those ideas and technologies? So this transition or this change is needed at all institutes. I work in innovation, R&D and commercialization of technologies. And in recent days, I do work in mentoring startups and even investing in startups. So the whole ecosystem has to start with the engineering institutes. That's my idea of having any good institute, engineering institutes. And anyway, the artificial intelligence is going to kill the teaching learning method that we do today. So we need new methods, and maybe instead of employment-based education, we will need a entrepreneurship-based education. So instead of taking a pride in what packages our students got, the institute might take a pride in how many startups were evolved out of that institutes. That time will come, but our focus need to shift there. And then innovation and R&D, especially field-oriented R&D, is the way to go. So here I'll be talking more about my experiences because I do have a lot of experience in R&D and taking it to a commercial level, exploiting the commercial potential of that development is what I have been doing successfully. And I'll share those experiences. And most of that work was done during or simultaneously when my academic career was there, when I was teaching, and also these professional activities and R&D activities were ongoing. So it's possible for all the faculty members to do something similar in their own area of expertise. Now, we talk a lot about climate change, sustainability, and solar energy. That's the topic the organizers have given me. So I'll be talking on that. My observation is many learned people do not have a very clear idea about carbon footprint, about the climate change, and what we call now global warming that is resulting in a climate change. So I just want to brush up the fundamentals a bit, and then so why the climate change is coming. A primary reason is a global warming, and why the global warming, and what we can do, what is our role in this. That's where I'll be coming. So just try to understand what is the greenhouse effect that causes a global warming, or understanding this carbon footprint that is way to sustainable lifestyle. So sustainability is for everyone at the individual level, at an organizational level, and how it works. Now let us understand what is the greenhouse effect. If I just give you this simple situation that a black pot is given to you and it is kept in the sun where the ambient temperature is 25 degrees. Now everybody knows black color absorbs heat, so it will keep on absorbing heat and the temperature will rise. But the temperature does not rise indefinitely. Like if you put a rice in that pot, it will not be cooked, because cooking will require at least 80-85 degree temperature, but the pot does not reach that temperature. Pot will reach something like say 40 degree, and then it will stop. Further absorption of heat will be there, but it will not heat up beyond that limit, may say 40 degree. Why it happens? See, this is FDP, which is interdisciplinary, and I understand it's not only restricted to mechanical people. So I'm just trying to simplify and make you understand the concepts. So why this happens? When the pot reaches something like say 40 degree, then pot becomes a hot body and pot starts radiating heat. So the heat transfer starts from pot to the surrounding, which is cold, 25 degree. So there are two processes happening simultaneously. There is a heat which is coming from the sun and pot is getting heated up. And there is a heat going out from the pot to the ambient or the surrounding. And that balance is met at some point, say 40 degree, and then it stagnates. So pot will not go beyond 40 degree. Now, this is how the system behaves. And this is how the equilibrium comes. Just imagine your earth in place of the pot. So there is an energy coming from sun, which is hitting the earth. Earth temperature goes up and it goes something like 10-12 degree kind of stuff. And then average, the year-round all location average. And then the earth being hot and the space being cold, there is a heat transfer from earth to space. And there is an equilibrium, and because of this equilibrium, the life is possible on the earth. So this is now what happens. What is the greenhouse effect? If this pot is put inside a box, say insulated box, and we put a glass on the top, then what happens? The radiation coming from the sun passes through the glass, it hits the pot and heats the pot. But the radiation going out of the pot, that does not go through the glass. It hits the glass and gets reflected and it gets trapped. So the glass, when you put a glass on the top, the radiation can come in, but it cannot go out. It gets trapped. Now, why this happens? It's because of the different wavelength of radiation coming from the sun, which is coming from some few thousand degrees centigrade. So those are the short waves that can pass through glass. But the radiation going out from the pot are the longer wavelength, just 40 degree temperature, or maybe in this case, say up to 100 or 150 degree. But that wavelength cannot pass through glass. So it gets trapped. And we can effectively use this principle for something good. Something good is something like this, where we can, it's a solar cooker. We can cook a food inside. because the heat is trapped, it remains inside, and the temperature of the pot will keep on increasing, and the food inside will get cooked. But this effect of using a glass is called as greenhouse effect. What does the glass do? It allows the heat to pass in one direction from a high temperature source, and it does not allow the heat from a low temperature source to go out. It gets trapped. So this is a solar box cooker or a oven that works on this principle. So there is an insulated box and a glass top, and maybe you increase a reflection using a mirror, so trap more sun, and all that heat that goes inside cannot go out. It gets trapped and it is used for cooking. Same thing is happening with the earth. The only thing is the amount of heat that is going out from the earth, small portion of it hits the greenhouse gas. Greenhouse gases are some of these, mostly 6 gases, but mostly it is the carbon dioxide. So carbon dioxide or these greenhouse gases, they work like a glass. So the heat passing through those molecules can come in, but when the heat is going out from the earth, and if it hits that molecule of a greenhouse gas, it will come back. In the Earth's atmosphere, the quantity of greenhouse gas is very, very small, not even in percentage, very small fraction. So it is like carbon dioxide, less than 0.05% all gases taken together. And that is why, because it is a very small magnitude, very small amount of energy comes back on the earth, it doesn't go out. And that is why the earth temperature is rising, but it is rising slowly, very slowly. But even that slow is very fast for the mankind. Like people, most of the people think that once we have a 2-degree extra equilibrium temperature, there will be no life on the earth. So that slow rise in temperature is also a very threat to humanity. So these are, which are these gases? These are normally 6 gases, major gases: carbon dioxide, H2O. What is this? H2O is a water vapor. Okay, methane, nitrous oxide. Then you have CFCs and ozone. All these are doing this. These are the gases, and this is a potential. I will not go into detail because of our time restriction, but okay, maybe this is a, what does this mean? This is a global warming potential. So what damage one molecule of CO2 can do, the methane molecule will do 23 times more damage, and HFCs will do 12,000 times or 1,300 times, or SF6 will do 22,000 times more damage in terms of global warming. But all other gases are very damaging, but their quantity as compared to CO2 is very, very small. And that is why we normally focus on CO2. And for other gases, we talk in terms of CO2, like CH4, that is methane. We will talk, it is 23 times more damaging or equivalent of CO2 potential. Try to understand our relationship, energy and environmental relationship. Normally, it is difficult. I have seen that it is difficult for people to connect energy-environment relationship. Most of them normally connect environmental activities with tree plantation, with water, save water, pollution related to air or water. Those are the activities normally people directly relate that they are the environmental activities. But in fact, if we are a technocrat people, and we should understand that major relation of environment is with energy. And this is how it is. Anything normally you do, you emit carbon dioxide. You do cooking, we are burning LPG or firewood or whatever fuel, you emit carbon dioxide. You are using automobiles, you are burning fuel, petrol or diesel, you are burning CO2 emission. You are generating electricity, even though there is a mix of electricity that you get something from coal, something from hydro, something from wind, something from solar, different sources. Still, majority of our source remains coal, more than 70% still, and then that is resulting into carbon dioxide emission. Electricity, when it comes from hydropower, many people think that it is pure or green. Not so. When it is a large hydropower, something like a Sardar Sarovar or these kind of projects, where thousands and thousands of square kilometer of land and forest is submerged, there is a anaerobic action happening on the biodegradable material, and methane is emitted. And in the last slide, we have seen the methane is 23 times more damaging than carbon dioxide. So these large hydro plants also emit, especially the reservoirs, emit methane. Hydrogen, many people think it is clean energy. Not really, because the water is required, which is using electrolysis, and electrolysis will use electricity, and that electricity in today's terms at least 70% is coming from carbon dioxide. And that's how the hydrogen, what we call clean, it is clean at the user end, but as a globe you are not, it's not clean. So almost all activities, if you think, you can think and you can relate, they are related to energy, and most of the time either it is a fuels, firewood, coal, petrol, diesel, which are burnt, or it is the electricity coming from coal. So all activities finally results into emission of carbon dioxide. And that is why if we talk about protecting environment, we have to talk about the energy, and that is why we are talking about the green energy or sustainability. This is how the relationship is to be understood. These are the carbon emission of some sources. You can just Google and find it out. Like petrol, 2.31 kg per liter of petrol, or 2.62 kg for diesel. For LPG, it is almost 3 kg of carbon dioxide per kg. Why I'm giving you this data is we need to understand the result of our activity. Like if I am burning 1 liter of petrol, indirectly I am contributing 2.3 kg of carbon dioxide. When I am using 1 kg of LPG, it results into 3 kg of carbon dioxide. Or think in a positive way, when I am using a solar cooker and I am saving 1 kg of LPG, I am reducing or I am avoiding 3 kg of carbon dioxide emission. That is how we have to look at it. And in electricity in India, this figure might be old, 0.85, but it might be 0.81 something today. So 1 unit you consume, because of the mix, something is from coal, something is from hydro and all that stuff. The emission factor at present is 0.85 kg of carbon dioxide per unit. So if you get a bill of 500 units, 500 into 0.8, so around 400 kg of carbon dioxide is released by your activity, your use of electricity. Now, how this carbon dioxide concentration on the earth has changed. For thousands and thousands of years, 450,000 years back to 1800, this concentration was varying between 200 to 300. In 1960, the recorded figure was 310. In my school days, I was taught that carbon dioxide in atmosphere is 0.03%. my son was taught, I think, maybe 0.035, and maybe my grandson will be taught 0.45, 0.045. So that's how drastically the things have changed. Like for 4,50,000 years, there was practically no change. And then in another 150, 160 year, it went up by 10 ppm. And then the rise is rapid. Now we can see from last October to this October, the change is by 2.5 ppm. That's very, very high. So this is how the carbon dioxide percentage in atmosphere is increasing. And earlier we have seen when the carbon dioxide increases, the global warming will increase because it will direct more energy back to Earth. It will reflect back more energy back to Earth. And this is how the concentration works. Unfortunately or fortunately, at present, we have only one mechanism to reduce carbon dioxide, and those are trees. What do trees do? They break down the carbon dioxide. They retain carbon and give out the oxygen. Again, from my school days till this time, everybody teaches me why trees are important, because they are giving you oxygen. That's a small truth, not really. It's very insignificant because oxygen in the atmosphere is already around 21%. And the carbon dioxide is only 0.04%. So even if all carbon dioxide is converted by trees into oxygen, my oxygen level will not rise even by 1%. So that's a small truth. It's a good thing that trees provide you oxygen, but you already have much more than you need. There is already 21% oxygen. The more important part that the tree do is they retain carbon. They break down the carbon dioxide and they retain carbon. They reduce the carbon dioxide levels in the atmosphere. That's a big thing that the trees actually do. Apart from the food chain, that your all food material or food chain is dependent on trees or the plants. Okay. So the more important role of trees is, one is a food chain, because it's all dependent on the trees and the plants. And the second is it breaks down the carbon dioxide. That's the only machine we have that can break carbon dioxide, retain carbon, and give back the oxygen. And that the process is called photosynthesis. You need for this process the solar energy as a medium. Now, what are these greenhouse materials? What do the greenhouse does? It is one-way traffic of heat, that it allows the heat from sun to go through, but it does not allow the heat from the other object to go back, or the low temperature object to go back. That is how it gets trapped. Normally, glass and plastic are the common material in our life where we can experience this. And another thing is the water vapor. I'll tell you how. There are some adverse effect of this greenhouse effect that you might have experienced in your daily life. Okay. Now, this is one thing I really don't like about online FDP, because I am unable to interact with you or unable to throw some questions at you. But okay, it will be dialogue instead of, it will be a monologue from my side. The two very common experiences I'll tell you. One is mostly when you park a car in sun. When you go and open the car after some time, the inside is very hot. एकदम भट्टी, अंदर आपको भट्टी का फील आएगा, इतना गर्म हो जाता है. Why? Because of the glass, that is windows and your front and rear glass to the car, the heat can go inside, but it cannot come outside. It gets trapped inside. it gets absorbed into your body, the upholstery, the inside structure. And then because it gets trapped, it cannot come out, it becomes very hot. So when you have to give some time, open the doors, allow some time to air to cool it down, that is a very common experience. Another common experience that you might have experienced is when there is a thin cloud. Cloud is not very thick. When there is a thin cloud or the very early cloudy days, you feel it's very hot. Technically speaking, you should not feel hot because the cloud is blocking the sun. Cloud is not allowing the sun energy, all the sun energy to come to the earth because there is a block. Why we feel very hot when there is a cloudy atmosphere? The greenhouse effect. The water vapor is a very good greenhouse material. So the cloud allows the sun heat to come to earth, but it does not allow the heat from the earth to go out. And because cloud is covering almost everything, almost all the heat radiated from the earth comes back. So there is a heat coming from sun through the clouds, and there is a heat coming back from the clouds, which is reflected. And that is why we feel very hot. That's a very practical example of greenhouse effect. And same thing you can visualize on a larger scale, that the whole earth is covered with that kind of cloud or a greenhouse gases, and then all the heat will be trapped on the earth, will result in a global warming. So this is this is how we should actually understand it. Okay. Now these are the positive effects of greenhouse, positive utilization of greenhouse effect. There are some greenhouses used in agriculture. Many people do not understand what that greenhouse means. Most of the people think that one green net or the shaded net that is used in the greenhouse, that is not greenhouse. That is just a net with a green color shade. Greenhouse is either made in this glass or plastic. So why? They trap the energy of the sun. So energy from the sun has to go inside, but it should not go out. Then what happens? That energy is utilized by the plant to convert, to break carbon dioxide. That is called photosynthesis. So greenhouse gas, greenhouse, when used for plants or growing vegetables, their growth is fast. The another use of greenhouse is for drying, like grapes and all. You see, they are put into the big plastic greenhouses. So you hang them, and then from grapes you make that kishmish. So that's how bedana or kishmish, jo bhi hum log bolte hain. So basically, you trap heat in a plastic greenhouses, where on a large scale you put grapes, and then that is a positive utilization. The solar cooker, the solar water heater, again, those are the glass tubes, but it's a double wall tube. Outside tube is transparent, which is using a greenhouse principle. Inside tube is black, which is absorbing the heat. So the outside tube does not allow the heat to go out, but allow the heat to come in. That is how it works. You know this guy, everybody knows him. Recently, he was in the news, not for good reasons. As unfortunately, we don't know how to treat our heroes. But recently, he was figured in Times Global 100 Environment Leaders. Okay, he's a good friend of mine. I have visited him a few times. Now, this tent, what that tent is doing, solar heated military tent, it's again a greenhouse effect. You can see half of the tent is black, half of the tent is transparent plastic. Now Ladakh is on the north of India, above your Tropic of Cancer. So apna कर्क वृत्त के भी ऊपर है, 34 डिग्री लैटिट्यूड है करीब करीब. So your latitude is 34, so sun never goes overhead. Sun is always on the south side. So how this tent is constructed? The transparent side is facing south, so the sun will always fall on the transparent side. The other black and insulated side is on the north. Sun never directly falls there. So the heat that goes through the transparent side gets trapped inside the tent. And then that heat is used to keep it warm, especially for the military. The temperature in Ladakh is very low in winters, and some military camps are at very high altitude, even in the snow. And I have seen these tents work even in the snow. So they trap the heat using this greenhouse principle. This is his school. Again, you can see on the top, there are two big glass enclosures where the heat is trapped. This glass and plastic, I think, combination they have. And from where the heat goes in and then it gets trapped. The buildings, you can see, the building part, even behind this plastic or the glass structure, there is a building. And the other two buildings, you can see big windows. The windows are big, almost from floor to the roof. The complete south side is all windows with glass. And the other view is from inside. You can see lot of light coming in through those windows, but it's not only light, it's all the heat also coming through those windows, and that gets trapped inside that room. So the room remains warm. And they do a lot of experiments, like in that cold weather where cultivating vegetables in winter is impossible because there is the snow or the sub-zero temperatures everywhere. And at that temperature, the plants cannot survive. But in its SECMO school, they have some such greenhouses where they cultivate some vegetables. Their average temperature remains around 12 degrees, while the outside temperature is normally minus 20 degrees. So this is how the greenhouse effect from sun is utilized positively. So it's not always that the greenhouse is causing global warming, bad for us, but once you understand the principle, you can use it positively. Unfortunately, in India, we have seen a lot of things we follow blindly. This is one big example. These are the commercial buildings in Mumbai. Most of these have architecture either copied or inspired from what is done in Europe. But what is good in Europe is not good in Mumbai because Europe is pretty cold. So they want lot of glass facades, and all the glass facades trap lot of energy, lot of heat inside. So the inside they have to use less heat to keep the building warm. In India, when we do this kind of stupidity, we spend a large amount of our electricity bills on air conditioning because there is so much of a heat coming in through these glass facades, which is getting trapped. And then you have to get that heat out using air conditioners. So like Mumbai, or I saw a lot of buildings in Gurgaon, so much of a use of a glass is actually running their air conditioning bills very, very high. So we need to understand, as an engineer, it's our responsibility to understand the behavior of this greenhouse material, glass and plastic. Whenever we use it in any application, how it will behave. Like in this application, it's a very, very negative impact that lot of heat is trapped in the building. And these are the cities in a very high heat zone, and they need air conditioners, and lot of energy will be used for air conditioning these buildings. Now, what is a carbon footprint? Carbon footprint, I earlier told you that anything now you normally do will consume some energy, and that will result into carbon dioxide emission or equivalent emission. Now, if you have some product like what is shown in the picture. There is a product, something like some maybe a cosmetic cold cream or something. But on this product, there is a mark here, like this black footprint and 100 gram of CO2. What does it mean? It means that while manufacturing this product, there is an emission equivalent to 100 gram of carbon dioxide. Okay. Now, why there are some countries in Europe, they have made it mandatory in some categories that the manufacturers have to write what is the carbon footprint of that product. Something like we write about the expiry date, or we write about the composition of a product, what is there inside the product. Similarly, some countries have made it mandatory. Many countries have kept it voluntary, but they prefer that manufacturers should write carbon footprint. In India, I haven't seen such products, but I have seen all our airline tickets. They normally mark what is your carbon footprint. Like if I have booked a ticket from, say, Mumbai to Delhi, maybe my ticket will have something like this, 353 kg. What does it mean? My contribution in that flight, because the flight from Mumbai to Delhi taking many passengers, but my contribution in those passengers will be 353 kg carbon dioxide equivalent because of the fuel and the other energy used. So for the product or for the services, people can calculate, estimate, and then put it on the ticket or on the product, what is the amount of carbon footprint. Now it can be for anyone. It can be for people, like a person like me, who was born in 1963, and maybe whatever life I have, maybe another 10, 12, 15 years. In that duration, because of my presence on this earth, because of my activities, there is a carbon dioxide emission, and this emission is my carbon footprint. I just talked to you about this gentleman, Sonam Wangchuk. He is the one who maintains a meticulous record about his own carbon footprint. वो अपना record रखता है पूरा. And what does he do? There is a site he has chosen near Kargil. At that site, he plants trees. The variety that he has chosen, that one tree in its lifetime does around 250 kg of carbon dioxide fixation. So that one tree fixes or breaks down 250 kg of carbon dioxide. So what actually happens? Whenever he does any activity, whenever he travels, say, by flight somewhere, and his carbon dioxide emission is, say, 500 kg because of that flight, he will make sure that there are 2 trees planted in that zone, and they are taken care for the lifetime. The people who are deputed to plant and take care of those trees, he pays their salaries and the maintenance cost from his pocket. So what he is doing actually, he is maintaining his carbon footprint record, and he is trying to do better than that, that he is trying to put more trees than needed, so that his carbon footprint becomes at least 0 or negative. That because of his presence on this earth, there is no additional carbon dioxide emission on this earth. So there are many people who do this. You might have heard about carbon trading. Like people who do renewable energy projects, they can get some carbon certificate. Because of that project, there is so much of emission reduction. And then somebody who has done some emission and he wants to nullify that, he will buy those. That is how the cycle works. For the event, there was one conference in Germany in 2011 where I had also some papers, and that conference was carbon neutral. They called it as a carbon neutral. What does it mean? There were delegates from 91 countries. So all those delegates traveling, In the conference, you have a lot of electricity use, you have whatever with the activities, that use, the travel, everything they calculated, how much carbon dioxide emission it resulted. They raised extra funds for the event, for that conference, and then they had put some solar and wind projects to nullify that carbon dioxide effect, equivalent. And then, so, but if they do not do this, that event will have some, maybe say 390 tons of carbon dioxide emission because of that event, because of the people coming there, participating in the event, and the energy consumption in that event. So there will be some figure, say 390 tons of carbon dioxide. So what they did some green activities that will reduce carbon dioxide emission more than 390 tons. So their event becomes neutral, carbon neutral, they call. In environmental terms, whenever people talk about carbon, it is normally carbon dioxide. Just remember this. When I say the event is carbon neutral, it's not the carbon neutral. It is actually carbon dioxide neutral. Okay, the carbon dioxide emission because of the event is nullified. Okay, that is how it means. Now, there are some strange understanding of people, like everybody understands electric car as a green car, green energy. Okay, now I just try to go to the root of it and make you one comparison. Say petrol car, if it is a 15 kilometer per liter, then we know now 1 liter of petrol consumes gives 2.31 kg of carbon dioxide. So it will be 0.154 kilogram of carbon dioxide per kilometer. So when I use a petrol car with this average, I emit 0.154 kg of carbon dioxide. When I use an electric car, say the car manufacturer has given me some specification or my experience, 20 units are required for 100 kilometers. Okay, that's the range, say. So it's a 0.9 kg CO2 per kWh, and I calculate, and then I find 0.180 kg of carbon dioxide per kilometer. So apparently people might feel that the electric car is good, it's environment friendly, but if these are the figures, then my conclusion will be electric car in this case is doing more damage than a petrol car. Okay, it's doing more damage to the environment than a petrol car. The only good thing will be the electric car emission will be in the cities where already there is a high emission from other sources. So localized effect of emission or the pollution will be less, but global effect will not be less, because it will be, the pollution will be in either different locations, like in Chandrapur or in Bhusawal or Kaparkeda, wherever you have a thermal power plants, the emission is there, but the car might be running in Pune. Okay, but now take a different scenario. There is a car which consumes not 20 but 14 units for 100 kilometers. Petrol remains same, but if the electric car consumes only 14 units for 100 kilometers, the emission comes down to 0.126 kg of carbon dioxide. Now in this case, the electric car becomes a better car than a petrol car. Okay, why I'm quoting this example is it's my way of thinking that as engineers, we should not make simple assumptions like electric car is better or LPG is cleaner. That kind of assumptions are not required. We can go to the root cause, we can find out the carbon dioxide emission, and then we can conclude which is actually better. And there are some misleading examples, like hydrogen is treated as a green fuel. At present, there is no technology available for hydrogen to be manufactured as a green. Okay, so hydrogen has to use electricity. Now, at least 70, I think around 80% in India is coming from carbon, that is coal. So you are using a coal energy as a electricity. From electricity, by doing electrolysis, we are manufacturing hydrogen, and then using that hydrogen in a car or a truck and calling that car or a truck as a clean fuel. Again, now once you understand this cycle, you will understand you are actually running not on hydrogen, but you are running on coal. Understanding this, those lobbies have now shift their examples. They are started calling the hydrogen as a green hydrogen, and then saying that the green part, that the electricity will be coming from solar or wind. Still, if it has to be an electricity and it is coming from solar or a wind, better go for electric car. Why you want to go in other way? Why you want to use the electricity for electrolysis, then using the hydrogen, storing the hydrogen, use a IC engine for converting the hydrogen to wheel power, straight away use electricity for wheel power using a motor. So the things are not as simple as they look on the face of it, but small thinking in the energy terms or in the carbon emission terms will help you to analyze what is really good and what is not. For our own carbon footprint reduction, there are only these principles. You have to reduce not only energy but also resources. What is resources here? I mean by resources, say I have 15 shirts for my use. That might be a reasonable number, like 5-6 t-shirts as a casual wear, 4-5 shirts for the formal wear, and 3-4 shirts for fancy shirts for some functions and all. Maybe as a general middle class person with my lifestyle, that 15 shirts might be a reasonable estimate. Then the 16th shirt, which is a resource, is a liability, because in making that shirt, there will be some emission. There is some carbon footprint associated with that shirt. So this is applicable to all resources. So it is not enough only to reduce energy consumption or shift to green energy. It is also important to reduce the resources, because every resource has some equivalence of energy and emission. And this is you have to follow for energy and resources. What? Reduce, reuse, recycle, and shift to renewable. So have a sustainable life. That is what. Now the second part I will touch is a sustainable lifestyle possible. Very yes. We are doing something for last few years. I will still not call fully sustainable, but reasonably yes. One of our solar friends, Dr. Janak McGillan Palta, she is in the news in social media these days. Some videos of her are getting circulated about her sustainable lifestyle. She lives near Indore. She is like our solar family friend. Now, what these experiences are, like we are using solar cookers since 1999. The one on the right with a small gap there was in 1999, and some 7-8 years back we have changed the reflectors. So this is the second set of reflectors. So first reflector we have used for 15 years, 17 years. And then last 8 years, there's the second set of reflector that is being used. And one on the left, that is the squarish dish that was introduced in 2010. So it's 15 years, but we have not changed the reflectors. Maybe another 3-4 years, it is still going to work. So we are using solar cookers, say it's 1999. Maybe you can see some video. So this is a bengan bharta kind of stuff we are roasting. Or this is, you can see the whistle, pressure cooker whistling. Now these are in a way easy to use. We do a lot of things with these solar cookers. We do omelets, thalipit, all vegetables, all boiling rice, milk, all boiling, roasting kind of activities. Normally, I make sure all my relatives and mostly my friends, when there are birthdays, I make solar cakes for them in these solar cookers. So there are a lot of things you can really do using these solar cookers. Then we have a biogas plant, which is working on a kitchen waste. We don't have a lot of kitchen waste as such, because normally people use with cow dung or some other organic waste. We don't have that. Is taken care by solar cookers, around 15-20% by the biogas, and the remaining by LPG or the induction stoves. This is a new development ongoing. 6-7 we have reached, where it is an indoor solar cooker with a photovoltaic panel and with a specially designed heat storage. We received a patent for that heat storage. And then we use a lot of other devices, microwave and the induction stoves. For me, they are also green because non-emitting, even though I'm using electricity, because there is a 5 kilowatt solar rooftop system. Now, because of a bigger family, this is not adequate, but initially it was more than enough. In fact, in a cold weather like what we have these days, or in those days, like in the month of January or February, the generation will be high, but the consumption will not be there. So my electricity bill used to be negative because we exported more energy than what needed. Then we are using solar water heaters. One was in 1999, and second, when the family grew, we added in 2012. Solar dryers, I normally keep experimenting a lot on my own. So I have one dryer. This was developed in collaboration, not in collaboration, for IIT Bombay. So they wanted us to develop one. This is what we did. But I have one at on my rooftop, and we do a lot of experiments. The best results I found is with the fruits. When you dry the fruits, the moisture reduces, but the sugar does not reduce, and the sweetness goes up. So like my grandson enjoys it a lot. We call it as a fruit chocolate. So your banana, if you dry there, the banana will be 4 or 5 times sweeter because the moisture goes out, the volume reduces, but the sweetness remains same. The sugar doesn't leave. And then this is a good substitute for sugar, because we call them fruit chocolates, because the kids like chocolates and all, and parents doesn't want to give them chocolates. So that's a good choice. That okay, dried fruits or fruit leather, that is a term used in Europe. They dry a lot of fruits, they become like a leather thing. All of us know about amba papad. Okay, am papad or amba papad. This is not actually dry like papad. It's like leather. The feel is like leather. But in Europe, I have seen many of my friends, they do this fruit leather of many other fruits, not only mango, but many other fruits. In fact, they don't have much of a mangoes, but they have other fruits, and they make this fruit leather in the different equipments, not only solar dryer, but other equipments, and they use it as a chocolate substitutes. And then at home, we have a lot of energy efficient devices, the fans, and the new device, whatever we purchase, we make sure it is at least 4 or 5 star. Just I was sharing all this just to give you some glimpse that it is possible to have a sustainable lifestyle to some extent. Okay, we for us it is possible to have to a very large extent. But I'm not very meticulous like Sonam Wangchuk to maintain my carbon footprint record and then see whether we are nullifying it or not. But I think it should still be reasonably okay, at least a carbon neutral lifestyle, because we have planted a lot of trees at our farm. Okay, then I share my journey of idea to enterprise. That's another master class that I take these days. As I said, my experience in this area of commercializing ideas. Now I am sharing with startups or the students and giving them some glimpses how to do this. So these are the different domestic solar cookers. Maybe I'm just giving you some glimpses. It basically started with this dish on the left, and this is a design by our German friend Dr. Seifert. The first thing that struck me was the stand is using too much of a pipe, so I just changed the stand. That was the very first thing I did with the design, and reduce the weight by 40%. Then I changed the geometry altogether. We just cut the circle, corners of the circle, and the central squarish portion. This was in a fabrication mode. It was packed in a box. But then further, this circle, we cut the corners and the central portion we are using. And then we developed a press dish. That's 4 components like this. Now, these are the evaluation processes because I have a mechanical and a production engineering background. That's where my brain works. But you might come with a different backgrounds. Maybe the computer or IT or those people can think of some apps, some monitoring devices, electronics, and other people can think of some trackers or control devices, data logging systems. It's all up to you where you put your ideas into place. What is important is the idea should get commercialized. It should go to the market. And this development finally standardized manufacturing in the dies. So dies costed around 30 lakh rupees in some 12 years back. But then these components were truly do-it-yourself kit. There are a lot of applications we saw, like in Indore. The lady on the left with the white hair, she is a Janak McGillen, whose video you may search on social media, you will find. And the other lady is another big name in environment, Dr. Vandana Shiva. And they inaugurated 8-9 years back, they inaugurated this solar tea stall near Indore. And a lot of people still visit just out of curiosity कि धूप से कैसे चाय बनती है देखने चलते हैं. And that fellow actually charges premium, the cost of the solar tea. So he saves on fuel and he gets more profit also. But there's the potential for a lot of such micro enterprises. In 2019, I did one expedition just to show how powerful solar cooking is. We did a kind of a world record of solar cooking at 18,300 feet in Khardungla Pass in Ladakh. I have a special connection with Ladakh. I have visited there 7 times, I think, 6-7 times. And I have many friends, personal friends also. And a lot of them do lot of work in solar cooking and other renewable technologies. That's how I'm connected. And this is a bigger version. In 2019, there was a national competition by Government of India about design of solar cookers. So we won a 5 lakh rupees award for this design from Government of India. This is for small community, cooking for around 50 people. Same design, but now this is again a do-it-yourself kit. A lot of old age homes and tribal schools are using it. In Himalayas in 2013-14, there were some solar treks organized by a team from Netherlands. So we provided them solar cookers, and they use no other energy than solar energy. So everything was cooked on solar cookers in high altitude of Himalayas in Nepal during the trek. This is a project in Uganda we did for one Med Vocational College, Lord's Med Vocational College. Again, the purpose of showing you is the commercial part of this design, that it is a do-it-yourself kit. I haven't gone to Uganda. None of us have gone to Uganda. We did not send anybody. The cookers were sent and they were assembled as per the manual by the local people and used there. And these cookers feed 350 children in that school every day. In similar project in Puerto Rico, we were in talks with United Nations about what can be done about solar cooking in case of disasters. And when we were actually discussing with some authorities, this was one opportunity came. In Puerto Rico island, there was a hurricane, Irma and Maria, those are the name of the cyclone, and everything was destroyed. And they had electricity lines down. They have a gas line also down. So they had no fuel, no electricity. And in that situation, somehow that the whole system worked. They asked for the cookers. Let us try here, and we could supply them cookers. I think five of them. They shipped it by air, and they put those cookers in different locations where in the relief camps and in the church, and the results were really good. They had no electricity, no gas. It was also coming from outside. The gas was supplied out. Gas and food was coming from outside, but then they experimented with this. So this also helped in disaster mitigation kind of situation. And then we have many projects with these cookers. You will find a lot of videos. One of my TEDx talk on this, and there are some wiki pages. A lot of stuff you will find on this. Another area that most of our faculty should do is there are technologies available, but they are to be implemented in real life situation. So here the research is not really big research. It is only a small research. Solar energy can be used for autoclaving. Autoclaving is the sterilization process. So this is a Dr. Mrudula Dravid, who was head of pathology and microbiology in a government medical college in Dhule. And they used these solar cookers or concentrators for sterilization in autoclaving, and they got amazing results. So, but then you establish that connection. And once that connection was established, there were some certifications. They got some awards for their research, some publications in the reputed journals like Elsewhere publication, Journal of Hospital Infection. We could do some pilot projects of providing these kind of systems for public health centers in rural area where normally electricity is not very certain. So they can use this kind of solar devices. And then the bigger pictures, we did a lot of big dishes, 25 square meter. And this was technology transferred to ATE group. All patents were licensed to them. They spent around 1.5 crores on our side and maybe another similar amount at their end. Normally, the development costs are not very big, but the commercialization costs are high. And most of the academics really struggle to understand that. Maybe if there is a time, I can talk on this. So these are those dishes. Then we did some design development work, not the execution, but this biggest 150-ton air conditioning system. This is what we designed for Gujarat State Electricity Corporation. This is a solar thermal air conditioner that is working on vapor absorption machines. I think biogas and all I just showed you, but we can do a lot with these kind of technologies like biogas in clean cooking in rural areas as a decentralized system. We got some national awards, runners-up award for these kind of innovations from Government of India. Then there are immense possibilities in India in a rural area where we can put this kind of a community biogas plants. Okay. This one is not community, this one is for a school, but it is for a bigger community like 400 children. And this works on a toilet plus food waste. So it's a both. Toilet waste is directly connected plus food waste is put through the inlet chamber. And this reduces their fuel consumption by 40%. Normally the similar blue person who doesn't understand, if you are not telling the person, he will not understand whether it is a LPG or a biogas. The flames are very similar. Normally the burners are also similar. And then there are some solutions those exist where there can be a centralized biogas and the pipe grid, something like a water supply grid, and individual connections to villages, to every household in the village. And there are some good pilot projects. Some early projects failed for some different reasons, but nowadays there are some really good projects where in those pilots at a village level, they have a centralized biogas and everybody gets a gas through pipelines and a meter for recording the consumption and paying for the gas. Then the another development that we do is these kind of a gasifier stores. They use briquettes, biomass briquettes. You can see a very clean combustion. It is coming from a firewood or a biomass briquette. There is a huge potential for these kind of technologies. Sometimes people might feel it's a criminal to use firewood, but there is it exists. Biomass exists in different forms. Like some manufacturer in our MIDC who are doing this farsan or namkeen production or wafers, the khawa from milk, or they are using these kind of systems. And there are some furniture factories in MIDC, so they get a lot of waste from cutting those plywood and all. So that waste they are using as a fuel. So they are not cutting actually the fresh trees, but they are using some other feed. But then from sugar factories, rice mills, from other cotton stake as a material, the biomass briquettes are formed. And these briquettes are also very good alternative for LPG or firewood. That's a green fuel actually. Nowadays we are working on bamboo as a fuel, green fuel. These are double burner biogas gasifiers, where the gasification system which converts firewood or a briquette into a gas is separate and the burners are separate. Normally the dirty work is outside the kitchen and the burners are inside the kitchen. And then recently, based on all these experiences, this friend of mine, Rahul Kulkarni, he put a lot of effort in developing this kind of roti maker machine, which is also working on a biomass gasification principle. So there is a big tawa, and this is used for in a hostel with 450 students. So the consumption is inside, and the outside atmosphere is clean, even though actually it is working on a biomass briquettes. And then we have some innovations in these are some of the projects which started as a student project. This was more like my PhD work, where I was doing solar multi-effect distillation. Again, my PhD was slightly different. It was not like a research problem taken up for doing a PhD. It was already the research work which was converted into PhD. So it was already ongoing research, and a lot of things were commercialized in that research. So one was a multi-effect distillation, the other was industrial oven, and the third part of it was that 25 square meter concentrator. And then we did some commercialized work for solar dryers, cabinet and tunnel type of dryers. Nowadays, the work is done on these innovations. It's ongoing work. I might have the only professionally run R&D unit in Dhule or in India. I haven't heard anybody having a private R&D unit, but this is what I do. This is what my passion is. So these are the concentrators, which are very close to a commercialization. Maybe next year people can see a commercial version. All patents are granted. We got different. We won some innovation grants around, I think, 15 lakh for this kind of development. Then this is the work I'm doing for Oxford University for last 5-6 years. They provided us the physics, and the actual construction and development we did. These are the different views. One concentrator is really huge, like the one on the left. That's an aerial view through drone. That's a 25 square meter aperture, but if you see the whole structure, it's an aperture, but it's an inclined concentrator. So the actual area is around 500 square meter. Like, okay, from the structure, there is a car parked on the side, and you can get idea about the size factor. So this is done for the Oxford University. It's close to commercialization again. The university will search for partners. That's my team. The other two professors work from Oxford, and I work from here. So these are different products and technologies that we could commercialize. Normally, as I said, my focus is not very typical academic research, even though I work for 31 years in academics. Mostly it is about the field orientation. So I write more into the commercial magazines and public spaces about the different innovations, different ideas. What I discussed till this time is mostly the products, but there are a lot of innovations in business models and financing models. So maybe I write in the newspapers also about these articles. One of these idea, सौर पंपाऐवजी सौर प्रकल्प ठरतील फायदेशीर. This was old, I think, how much? February 2015. Okay, agro one. So This was adopted by government of Maharashtra in as a agri solar feeder. So instead of individual pump, they do agricultural feeder on solar energy. While I was in the institute, a lot of my colleagues know we used to do some kind of promotional programs like solar canteen and all. Then we do a lot of workshops for this technology dissemination and transfer and training. Most of these are hands-on workshop, and sometimes some friends from other countries also come as a participant. Nowadays they come as a resource person also. We have one such training workshop on 23rd January in 2026. The person in the center, one Mr. Professor Celestino, he has his own designs, and on this 23rd January workshop, he will be teaching those designs. And then some conferences that we do, but they were truly international conferences, like World Solar Cooker International Conference we did in 2017. Around 40 countries were participating. So I was one of the 4 main organizers here. And for the other institutes, all the engineering institutes, what we do nowadays, what I do actually is I conduct master classes on this idea to enterprise for research scholars, faculty members, and students. Many people have the idea many times starts with projects or mini projects, but then after the project exam is over, it ends there. There are many ideas which have the potential to commercialize and to make some kind of a business or enterprise out of it. So I do those master classes, how this should be done, how it is done. For research scholars and faculty members who want to do their PhD or MTech, I give some ideas about what can be different projects. And then we can help them in availing grants in sustainable technologies, because I got a lot of grants myself. But most of them were innovation awards, not actually grants. This concept of technology readiness level is what everybody should understand, but I think I don't have a time to discuss this slightly offbeat area. So I'll just stop, but I'll just showing you some glimpses from where the money can come in for research and commercialization, the innovation, research, and commercialization. These are some international and national agencies from where the money comes. So this is the International Solar Alliance. Then you have Wiki's Climate Launch Prizes. BIRAC does a lot of things. We got some 15 lakh rupees from BIRAC for those inclined concentrators. Then small grant projects, International Solar Innovation Council. Again, we got some 4 lakh rupees from them for indoor solar cooker. Then government agencies do different competitions. This competition, one of the competition was won by Indian Oil Corporation. The company was Sunbucket from USA. And then in India, all the trials and development work we were doing for Sunbuckets. So there are a lot of openings where you can get this money. Nowadays, we can get a startup funding or angel investors or venture capitalists like the Shark Tank, everybody knows. There are some other platform. One is IPV, and there are other groups. I think I'll stop here. We should give some 10 minutes for the discussion or any questions if they are there.
Yes, sir. Thank you for a very interesting presentation with actual examples and photographs. I never seen any paragraph or some writing related to your presentation. So all the presentation contains actual photographs and actual applications. So I think it's a really nice presentations for our participants. And you covered all the topics like emission of the greenhouse gases, then understanding of greenhouse effect, utilization of greenhouse effect, carbon footprint for the product and the peoples, and how to reduce the carbon footprint. That also you covered in your presentation. Then various applications of solar cooker, various designs of solar cooker, energy efficient measures as our daily routine, then biogas and its real application, real-time application, biomass. So I think as per our title, solar energy, sustainability and climate change, you covered all the topics related to our FDP title. So thank you, sir, for your nice presentation. Now I would like to ask participants, it's a good time to interact with our great speaker, Dr. Ajay Chandak, sir. So if you have any queries or if you want to interact with the sir, so now the time is open for you. You can unmute yourself and ask the question.
Sir, there are some questions in the chat box.
Yeah, better take them first.
Yeah, CO2 emission from petrol and petrol, diesel, LPG per liter shown. Is it per year or how it is?
No, you consume 1 liter, you have that
Yeah.
emission.
Yes, sir. It is like if you consume 1 liter, it will produce the whatever the
Yeah,
mentioned.
you consume LPG in 1 minute, you release 3 kg CO2 in 1 minute. You consume in 10 days, you release 3 kg in 10 days. So
Yes, sir. How electric car will emit 0.9 kg of CO2 per kilowatt hour?
this is called as an emission factor. Like electricity that we use, it comes from different sources. Like solar, wind can be treated as a clean source, but the coal is not clean source. Then even hydro project have some emission. Gas turbines have some emissions. So taken as an average, weighted average of the whole mix, that is decides the emission factor. Now I'll tell you this emission factor was around 0.95 a few years back. Now because the solar contribution is increasing, the factor has come down to around 0.79 or 0.8. So when you consume 1 unit of electricity effectively, because we don't treat it as all dirty energy, some energy coming from coal, but some energy coming from other sources. So how much that contribution is, and that contribution is announced every month by Central Electricity Commission. So that is the emission factor we call. So if you just Google, you will find that. So when you consume 1 unit, equivalently today's terms, you are emitting 0.8 kg. When solar contribution will increase, it might become 0.7, it might become 0.6. For a country like Costa Rica, it is 0 because they get all energy from green sources. They have a very good hydro potential and small hydro potential and the other clean sources. So Costa Rica is a country where they don't burn coal.
Yes, sir. These all questions were from Dr. Avinash Patil. Now the third question, sir. Nayan Jyoti Talukdar, she's asking, sir, can we raise the temperature up to 400 degrees Celsius using a parabolic dish collector for
Yes.
moderate radiation of 600 watt per meter square average?
Yes.
Yes.
Yeah. Solar concentrator is my area of expertise, or you can say super specialization, where I do consultancy even to the Oxford University or UIUC, or we do work for them. You need a point concentrator, one, and depending on your heat load, how much quantity you want to heat in what time, the size of the concentrator will be decided.
Yes, sir.
Okay. But it is very possible. Nowadays, there is one company called Sunrise CSP, which has adopted one Australian National University design. It is a huge concentrator, 500 square meter. That is 5,000 square feet. So in Pune's term, maybe equivalent to 6-7 flats. That's the area of a dish. And they have a temperature at the focus around 2000 degrees.
Yes.
So temperature is not an issue. It depends on the size of the concentrator and the concentration ratio that it can deliver. One more interesting case I can discuss. I generally like to travel and see new things in my domain. So in that connection, once I went to France because they had some solar furnaces. And there is a furnace in northern France, which is 30-year-old, 100-meter square area. And they were able to deliver 3,000 temperature, 3000 degrees centigrade. And near to that place, there is a place called Odilo. If you just Google, you will find those pictures. That's a big furnace constructed within the wall of the building. And they were able to deliver 6000 degrees in the focus. And there was another furnace which available in the public domain because they are using it for the military and the space application. But we could see that because the director was connected through some friend, and that furnace delivers 12,000 degrees. So that's the kind of the things happening in the world, the people are doing in the world, that they can attain 12,000 degrees in a solar furnace, and they're using it for space and military applications.
Sir, few participants, they are looking for to participate in your workshop. I request you to kindly share your details to us, sir, so that we can connect with
the last slide had the details. Maybe you can share my email, no problem.
Yes, sir. Yes, sir. Sure, sir.
You can share my email, my phone number, no issue.
Thank you, sir. Dear participants, if you have any queries or if you want to have the collaboration with Dr. Ajay Chandak, sir, please you can have the question answering.
Yes, I think, sir, we will stop here. Thank you for your nice interactive presentation and informative presentation. So in future also, we will try to connect for the different with the different programs. So it will be helpful for our faculty members and research scholars. Thank you, sir.
Thank you. I think we are just in time. It's
Yes,
8 o'clock, so you can proceed with the further.
Yes, thank you.
Thank you.
Thank you, sir. Dear participants, now we will have the 5 minutes break.
Sir, Kumar sir is here.
Yes, yes, sir.
Biradar sir, Kumar sir is here.
Yes, sir. Sir, am I audible? Ajay sir, am I audible?
Yeah. Madhu, yes, you're audible.
Yes, just 2 minutes. We will.
Yes, okay, no problem.
Rejoin.
Yes.
Dear participants, we will have a 2 minutes break. We will join at 8:03. Yes, sir. I think we can start now.
We'll start. Now it's a time 8:03 p.m. So we'll start. So once again, welcome to all the participants. First day, session 2 for this 6-day online FDP. Now we are having with us the great personality and the innovators, Dr. Ajay Yadav, sir. The topic is recent development of solar air heaters. It's my pleasure to introduce Dr. Ajay Yadav, sir, as an accomplishment and research in the field of mechanical engineering with distinguished careers, specific industries, academia, and researcher. Dr. Yadav completed both his MTech in 2008 and PhD in 2013 from the prestigious Indian Institute of Technology, Kharagpur, specializing in the advanced thermal science and the fluid engineering. He is currently serving as an associate professor in the Department of Mechanical Engineering at IIT Patna, a position he joined in 2022. Before joining IIT Patna, Dr. Yadav served at NIT Karnataka, Surathkal, for over a decade, where he contributed significantly as an assistant professor from 2009 onwards. His rich and diverse research expertise include superficial fluid heat transfer, CFD, bioheat transfer, solar energy, and internal combustion engine, and refrigeration and air conditioning. Dr. Yadav has an outstanding research profile, over the 100+ publication in reputed journal and the international conference. He has successfully supervised 10 PhD scholars and 30+ MTech students, contributing immensely to research and academic development. He has also led 6 sponsored research projects with a total funding of 1.5 crore, supported by the leading agencies such as DST, SERV, and VGDST, reflecting his strong reputation and the contributions in the research community. Before his academic career, Dr. Yadav served in the Indian Navy for 7 years, where he worked extensively on IC engine, steam power plant, gas turbine, refrigeration and air conditioning system, pump, compressor, and various engineering machinery, being a rare blend of industrial and defense and research experience. We are honored to have such an eminent personality with us today. So I welcome Dr. Ajay Yadav, sir, for his expert session. Sir, welcome for this particular session. Now the time is yours. Thank you.
Sir, you can stop sharing so that.
Yes, sir.
Okay. Okay, thank you for the introduction and good evening to all of you. Can you see my PPT? Visible?
No, sir. No, sir. Only we can see the people in presentation. It is not visible, sir.
Okay, just wait. Sharing.
Share the screen.
Oh yeah, okay, we will see. Do again.
Share the entire screen, sir.
Now it is it? Just check.
Yes, sir. Yes.
Visible?
Yes, sir. It is visible, sir.
Okay. Okay, so good evening to all of you.
Good
And
evening, sir.
today my topic is recent developments in solar air heaters. This work was done by one of my PhD students, Dr. Nidul. So the similar or what he did in PhD that I'm presenting here. So Dr. Nidul is now in Manipal University, MIT Manipal. So in this, actually, I'll talk mainly on these two topics here. Study of triangular duct solar air heater with V-ribs as artificial roughness. And another one is semi-cylindrical side walls. So solar air heater with semi-cylindrical side walls with W baffles and multiple discrete inclined baffles, this type of different turbulence generator, you can say, or turbulators. So these different types of fins we'll talk. So overview of the talk will be on the first introduction part. And then solar collectors. In that we'll talk about the classification, artificial roughness in solar air heaters, duct cross sections. There are different types of cross sections, and the effect of cross sections we will talk here. Then methodology is a numerical and experimental. So both we'll talk. Numerical part is more here, experimental is less. So then results and discussion, triangular duct solar air heater with V-ribs as artificial roughness. Those, that is one part. Another is solar air heater with semi-cylindrical sidewalls. So this will be the overview of the talk. Then we go to the conclusion part. Let us talk on this, what is, why it is required, the solar energy research mainly. And most of you are aware of the renewable energy. And as per, if you see this introduction, what I put here, as per the International Energy Agency, global energy demand is expected to rise by 5% yearly. Okay, and this will increase the 5% CO2 emission as well. Because we are more dependent on the fossil fuels, which mainly generates CO2 emission. So the thing is, and further, if you further the pace of economic growth, that is also accelerating, actually day by day increasing. So it was not going to be 5% only, it will increase. So that so energy demand is more. So we have to somehow generate somewhere energy. So that energy, just hold. Yes. Can you come after something? My talk is going on. So these are the, so we have to, dependency on the fossil fuel have to reduce, and some renewable source we have to find. So if you see other things as a result of this, it is anticipated that global ambient temperature will rise by 2 degrees. 2050. 2050, we are taking the reference 1900. Okay, 191900 here. So around this will go 150 years, it will 2 degrees Celsius rise. In addition, the implication of accelerating demand and decreasing reserves of conventional resources will be an escalation in prices, perhaps even higher than the inflation rate. This, you can see the data from the climate.gov. You can see here if you take the 1900 as a year reference, around 0 if you consider almost. And if you come here, it is 2020 is coming around 1.5 degree. So it will be 2050 maybe 2 degree in that way. Now, if you talk about India, in India, gross petroleum imports and the fossil fuels, we're talking gross petroleum part imports in 2021 was 19% of the India's total imports. And coal directive, if you check coal directive 2020 to 21, India is the second largest importer of coal. So these things are talking about the fossil fuels. In the context, during the last 2 decades, there have been a worldwide research and development effort in renewable energy resources and systems. So renewable energy, actually the research, one is this side, solar side, another side, if you go the biomass and those. So biomass is a, you can say in the short term, it is getting renewed. So that's why it is renewable. Otherwise, the coal is also getting renewed in the long term. But that won't be renewable. It's long, it takes so much time. If you are doing in short term, 2 years, 3 years, you are growing some plant and that consumes oxygen, CO2, and it grows carbon, and its wood will grow like that. So carbon content will increase. Again, you burn and you'll get CO2. So this is the cyclic thing. So this way you can say renewable, that biomass side. So solar is directly you are getting, actually this is a green energy. So according to IEA Renewable Energy Market Update 2021, renewable capacity addition surged by 45%, with the renewable contributing 90% globally to new power capacity expansion. So this side we are going very fast to expand the infrastructure related to the solar energy or renewable energy. Among the renewable energy sources, since prehistoric times, the benefits of solar energy has been realized for application such as drying and preserving food. This is a very important part of the solar air heaters we are talking mainly. This is used in that. Direct solar energy with the highest potential can be harnessed for wiring applications in different forms. So there are different applications of air heater. So the solar energy application, if you talk, there is a different. This mainly we are talking about today's talk in solar air heater. So what is the application of solar air heater that we are talking? So hot air, see this application will be generally in the medium, low and medium temperature application. Okay. Drying of agriculture products for a developing nation where agriculture forms the economy backbone. Drying and preserving farm harvest is of prime importance. So this drying and preserving the agriculture products, that is very important to keep for a longer duration. So because these are mostly perishable products, so that drying part, if you dry and keep it, it can be kept for longer duration. So that is, as solar air heater is very important for that. In that you can use indirect type solar air heater, direct type solar air heater, those things are there. And other application is space heating of a building. So in the that depends on the requirement of the building temperature, what you want to maintain in that. If you want higher temperature, you have to supply some energy, hot air. So hot air can be supplied using the solar air heater directly. See the difference why that people can think why we cannot use direct heater, electric heater to heat the space, air inside the room. Maybe mainly required in winter season. See, one thing is if you are heating directly using heater, electric heater. So how you are getting the electricity first thing? So you may use the fossil fuel to burn a fossil fuel and burn those fossil fuel and get the thermal power plant in that power generation will get. That is again the pollution will be there. Even we are using electric heater, but somewhere CO2 pollution is there. Another thing is you can use PV cell, photovoltaic cell. Okay, photovoltaic cell has efficiency of around 18% to 20% in this range, 15 to 20% you can say. So 15 to 20% efficiency, you are getting suppose 100 watt from solar radiation directly, and you are utilizing only 15 to 20%. 15 watt you can say, 20 watt. If you use in that place, don't use PV cell, use directly. If you are, because your application is to heat the air, you need heat actually. So why to convert into electricity? That conversion efficiency is not good, PV cell efficiency. So directly you can use solar air heater, thermal collectors. These has efficiency around 60% in that range. Thermal collector, if you go, different types of thermal collectors are there. If you use liquid type, you'll get more higher efficiency. So you are getting 60% in that range, and here it is 20%. So you can see the 3 times higher you are getting. So why to use that PV cell and do this? That is not advantageous. Okay. So even in the case of solar water heater also, solar water heater, if you use the PV cell and use that heat electricity and heat the water, but in that way you are getting only 20%. If you do directly heating, no conversion from heat to electricity, solar energy to electricity, then directly you are going to get 70% in the water case around that. So 70% efficiency here, 20% efficiency. This much gap is there. Better to use that directly. So now we'll talk about the solar collectors. What are the different types of solar collectors? Okay. Let us see this. These are our solar collector. We manufactured it, fabricated it at our NITK earlier lab, where Dr. Madhuganda Viradar also worked on this. He worked. So this is supercritical CO2 waste flat plate collector. How flat plate collectors looks like, that I put here. So the supercritical CO2 very high pressure required here, around 100 bar pressure. So this is mainly, you can say, the liquid type. Even the supercritical CO2 is in that, in between the liquid and gas phase, mostly the gas phase, you can say. Other one is from this is widely used solar water heater, evacuated tube type. So first one is flat plate collector, another is evacuated tube collector. This is third one, parabolic trough collector. So parabolic trough, you can see that, and if you want higher temperature, this is here you can supply air or water or whatever. So this is parabolic fluid you can collect and circulate, and here you are getting the concentrated solar energy on this tube. So this is called parabolic trough, higher temperature you get. And above that, this type is also there if you want very high temperature. Okay. So you can see this much area and concentrated focused would be there on this only small part. So this much concentrated heat source heat you are getting here. So solar radiation, the solar rays will it will focus on this focal length. It is kept here, and you'll get the higher temperature. So these are the 4 types. These 4 types: flat type, evacuated tube, parabolic trough, and this type. In this all, if you see the temperature range, why we need this type, different types? Because we have the requirement of different temperature. So flat plate, you can get around 80 degrees Celsius. This is the approx it is given, plus minus some 10-20 degree you can go. So this is the flat plate, 80 degrees Celsius. Evacuated tube, if you go 180 degrees Celsius. Parabolic trough 400, and this type maximum temperature 900. So this is the range of the operating temperature. Other thing is, if you are getting higher temperature, it does not mean that you are getting higher efficiency. Efficiency is just a reverse of this. If you need higher temperature, then losses also will be high, because losses to the surrounding temperature is fixed, 300 Kelvin or 27 degrees Celsius or 30 degrees Celsius, in that range. And as your fluid temperature is increasing, solar collector plate temperature increasing, then that temperature difference matters there for heat transfer. If temperature difference is more, your heat transfer will be more. Simple. So losses will be more. This thing you can see the research paper. This is the one research paper, effect of temperature on efficiency. As you go on, increase the temperature up to 400 only. See, this type, if you use 900, it will go. You can imagine that how much efficiency you are going to get, very low efficiency. So if it is the temperature is in this range, you can say around 50 degree, 60 degree or 80 degree, you are getting around efficiency around 70 to 73 in that range. As you go on increasing the temperature of collector or fluid temperature, if you want higher temperature, your efficiency will drop. Okay, so that depends on the requirement. Okay, if you need that 900 degrees Celsius, then what you can do? That is your requirement, then efficiency will be less. But whatever it is, you will get more than that PV cell efficiency. PV cell efficiency is 15 to 20% only. That's the problem. Okay. Now let us see we'll talk about mainly here the flat plate solar air heaters. The requirement here, we use air for either room heating. Room heating, what will need that? Generally 30 to 40 degrees, 40 is much higher. You can say in that range, 30, 40 degrees Celsius. And if you want to use it for agriculture product for drying purpose, you may need 80, 90 degrees Celsius in that range. So you will get 80, 90 degrees Celsius in flat plate solar air heater. So you can see this, if a heat exchanger in which this is flat plate, how it works, that is, it is mentioned here. Incident rays, sun rays is transferred as heat energy to the air. It's a simple thing. And this is very simple in construction with no moving components, fixed in a position, and sun tracking is not essential, unlike concentrated collectors. In concentrated collectors, that is essential, sun tracking. If you don't use sun tracking, then that radiation will not, if it is not parallel, then means you can say if it is not it is not focusing towards the sun, then this will deflect somewhere else. It will not fall on the focal. So that is a problem in the case of concentrated solar collectors, parabolic, dish type. Okay. So in that case, sun tracking is mandatory. Here, if you do sun tracking, your efficiency will improve, but it won't become zero. Okay. So if it is not 90 degree, okay, perpendicular to the sun rays, then also you will get some efficiency. Okay. So most of the solar water heater, you might have seen that there is no tracking. This is fixed. The south facing, it is based on that some latitude, that area, and some angle you have to give based on the fluid also. In an air case, angle requirement is very less, so almost flat, perpendicular, you can say almost perpendicular to the sun rays. Okay, so unlike PV cell you should keep always perpendicular to the sun rays. Okay, but in the water heater you will not find that perpendicular always. That you need some angle, higher angle actually, so that it should get some buoyancy. Okay, so height is required. If you keep that flat, perpendicular, sometimes flat, if it won't work in the case of water. Viscosity is more, that needs some buoyancy effect, okay, to move that natural convection. So what is what it consists of? You can see the solar air heater. You see this first figure, air inlet here, like box type of structure. Okay, simply box you can say here. And solar radiation is falling on the top surface. And top surface is what? Here you can see the second one. Top surface is a transparent, first one. You can see the top one is the transparent part. This you can use glass or some other material which should be transparent. So then in between there is a vacuum, then below that, there is a absorber plate, collector you can say. So this absorber plate and this transparent plate, these are in between, there will be vacuum. Vacuum maintaining is not easy. So if you maintain this vacuum and seal it properly, maintaining not required. Once you fabricate it, then you see that it is vacuumized, then you seal that. But sometimes it gets damaged or something, then there will be problem that. So if there is no vacuum, then your efficiency will drop little bit drop in efficiency. Okay. So this is the thing. Here you are putting absorber plate. This will get heated. Absorber plate, because sun rays coming directly from the vertical here, you can see, crossing this transparent cover, then it is falling on the absorber plate. Absorber plate will get heated, and below that there will be airflow, which solar air heater, air flowing it, so air will get heated by this absorber plate actually. So, and below that there will be, these are the insulation. There should not be heat loss to the surroundings from this side. But top side you cannot insulate. Top side there is a glass, transparent glass. So transparent glass, through this there will be heat loss. But the thing is, if you vacuumize properly, there is a reduction in the significant reduction in the heat transfer through the top surface also. Okay, if you don't vacuumize properly, then there will be loss. Okay, so still it won't be that much. Okay, so that part is, as your as I told earlier, this absorber plate temperature is increasing, suppose, then your losses towards the top side will be more. That is the losses from the top side mainly. This side you can increase the insulation thickness and you can reduce the loss, bottom and side walls. So let us go to the classification of flat plate solar air heater. What are the different types of solar air heaters? So the simplest type is, you can see this is the simple one, first one. There is no vacuum here. So what we are doing, transparent cover, we are putting some glass or some different materials also you can put here. Sometimes some plastic type of materials, so people are using. Okay. So here you are putting, and air is flowing here, and this is your absorber plate. The absorber plate is metallic and mainly black chrome coated on that. So absorptivity should be close to 100%. Okay, 95 to 100%, in that range absorptivity. So this will absorb the solar radiation and this will get heated. This plate will get heated, solar plate. Solar plate means absorber plate. This plate will get heated, and what the air is coming through this, in this passage, this air will get heated through this absorber plate, not by this transparent cover. Transparent cover will not get heated. Okay. This transmissivity will be almost close to 100%. Okay. So this will not get heated. Now the thing is, what happens here, when air passes through this channel, air gets heated, and this air, hot air you can say, will heat this transparent cover also. And from here, due to conductivity, this will there will be heat transfer to the surroundings outside. So that is the mainly loss. Okay, here. If you go to the second one is what? The similar type, this air absorber plate is there. In that, there is a from the top there is a flow, and from the bottom also there is a flow in the absorber plate, both sides. So you are actually utilizing the double area, you can say, of the absorber plate. Okay, above side also, bottom side also. So double area, UA delta T, if you calculate, you will get more heat transfer, total heat transfer, you can say, that way. So the temperature increase will be less here. Temperature of the absorber plate will be less. Now the third one, if you come here, this was what I was discussing earlier. So if you put vacuum here, this part, then losses will be less. Then air flow rate, you can see air is flowing through this, and the losses in this case will be less. This is the third type. So the thing is, depends on your budget or requirement. You can use the simple one. also. This first and second type vacuum, if you cannot, this easily you can manufacture first and second type. Okay. Let us go to the artificial roughness in solar aerator. What are the different types of artificial roughness and why it is needed? First thing is why it is needed. A solar air heater, air flows through the duct, but you know that the air thermal conductivity is very less, and which causes the lower thermal efficiency. The thermal conductivity is less, and convective heat transfer rate also will be less in that case. The observer plate. So due to these things, there will be thermal efficiency. So how to increase this thermal conductivity? How to increase conductivity? Increasing, you have to mix something in that air. Then thermal conductivity of air, how will increase? It is a fluid. Other thing is convective heat transfer. You can increase by changing the velocity, by changing turbulence in that, making the flow turbulent. So there are ways to change that convective heat transfer part. Okay. So in that, how to change? Conductivity changing is difficult. Okay. You need fresh air you want, you are mixing something in that will be the problematic then. So that part is different. We'll talk here the easier part, which can be increased here. This part is the lower convective heat transfer, increasing the convective heat transfer. So how to do that? We will put some turbulent creator, generator, you can say. So the thing is, second part, if you see here, second point, development of the boundary layer and increasing thickness of the laminar sublayer over the hot absorber plate leads to higher thermal resistance, and subsequently heat losses increases. So when the boundary layer forms, you know that when the boundary layer forms at the leading edge, there is a higher heat transfer coefficient, very high you will get, highest you will get there only. After that, as boundary layers increases, thickness increases, that actually creates the resistance, thermal resistance, you can say. And your heat transfer rate, convective heat transfer coefficient will decrease. So what we want actually here, we want to break that laminar sublayer. We want in between, it should not be the only one boundary layer. It should break again, form, break and form, so that when it will form a starting part, leading edge type of things, you can say. When the boundary layer starts, that point actually in that zone, your heat transfer will be higher. So you need to do that actually. That boundary layer you have to break. So for that, what we should use? We should use fins, something in between. Okay, artificial, that is called artificial roughness. Fins, what we are putting in between, that you are actually resisting the flow actually. So in between, you are putting some fins in various configurations. Okay, so these configurations are different. We will talk. This is called artificial roughness. We are putting some roughness in that duct actually. So duct is mainly part is your collector part. In that collector, you are putting some fins. So that will create additional turbulence and disrupt the growing sublayer of the boundary layer. See that how you can put here. There are two configurations it is put here. Schematic representation of the finned plate solar aerator. There are fins you can see. Small you can see here. Okay. Transparent cover. Then and this is observer plate. In that observer plate, the bottom side of the observer plate below side, you can see that there are fins. Many numbers of fins are there. So when flow takes place here, this will come and it will disrupt the boundary layers. So it will pass through that, again it will form, again break, new boundary layer will form, like that. So in that case, you will get higher heat transfer coefficient or heat transfer rate finally. There are different types. This type, corrugated type also you can use. So There are different types of reefs, this is artificial roughness that we will talk. Now the thing is, if you are putting these things, what is happening actually? Your pressure drop will increase. If you are using here some fan, a small fan you are using, and this fan initial power, if there is no roughness or no fins, there will be smooth and easy to flow. So power requirement will be less because delta P will be less. Now the delta P will increase. So there are two things. One place delta P is increasing. Another thing, your heat transfer rate also increasing. Muscle number is increasing. So there are two things. So how will trade-off between these two things? There is a parameter. Okay, that is called THPP, thermo-hydraulic performance parameter. Thermo and hydraulic both will take care. Okay. That parameter we'll talk later. So main part is last line. If you read, if you see this, the main objective is to enhance the heat transfer rate with a minimum possible increase in pressure drop. Okay. Now the thing is, this whatever you want to put their artificial roughness. Here it is circular. That earlier one it was shown here. Here it is rectangular type. Small see, you can see this fins, rectangular type. So that same thing, if you put circular or rectangular, whatever it is, but the height of that height, you can say this height, E1, E2, that you have to see that based on your Reynolds number, this height will be different. Okay, this will vary, and it should be, suppose it should reattach. Actually, this is the reattachment point. This is breaking and reattaching here. Boundary layer breaking due to this, and this reattachment, and again boundary layer is forming. This is important. Where the boundary layer is forming on reattachment point is where the reattachment is there. That place there will be highest heat transfer coefficient. That is important point. So reattachment is very important. So you can see that based on your Reynolds number, you will see that whether reattachment is occurring or not. This is the important part. Here you can see this. This is bigger size. If you use, there will be no reattachment. Here there is no reattachment. Third and fourth case. Sorry, fourth and fifth case. So this way you have to do the studies and you have to optimize your configuration based on your flow rate. So this range is given here. In this range you should operate. Based on the Reynolds number, actually, what is the general normal Reynolds number is there. Based on that, it is optimized to this range. 0.03 to 0.05 should be the relative reeve height. What is the relative reeve height? Reeve height divided by the diameter. E by D is the RH, you can say. So reeve height divided by diameter is 0.03. It is around, what is this? Around 20 to 33 times, you can say. So 20 to 30 times less that height of the roughness. Now the thing is, distance also matters. Okay. So these things, distance means pitch, you can say, one roughness, one artificial roughness to the another one. This is called reeve also, reeve pitch. Okay. So from here to here, what should be the pitch? That also depends on the various factors. Okay, and one is Reynolds number. So you can see here, if you put the very close, if you put close, you can see there is no reattachment. There is no reattachment. Here also no reattachment. Here it is there, like this. So reattachment must be there. That is the main our focus on that. So this, you can see this should be 9 to 15 times relative reeve pitch. So this relative, this height, 15 times of the height you can take. This is the pitch. 9 to 15 times, and so you can say in between you can take. Now another thing is impact of reeve inclination. Okay, reeve inclination on the flow pattern. If you this you can see the inclination. If you keep the just vertical to the 90 degree to the flow direction, then this type of secondary flow will not generate. If you are putting inclined, then what will happen? What the flow is coming from this side, some flow will start moving in this direction. So that is called secondary flow. So the study on secondary flow also people have done. This is important part. This enhances the efficiency. So there is a 60 degree, 45 degree, depends on the what different types of ribs we are using. Okay. Then in between there is a gap also. This another one you can see. This secondary flow as it is flowing through this, and if there is no gap, what will happen? This side it will jump from here, and this side temperature will increase. Here, if you are allowing this to move, so this secondary flow will go out from this easily, and then again the another secondary flow. So what is happening actually? This secondary flow is taking heat from this side, this zone, and taking it and going out. So this way, this zone temperature also won't be very high. So actually, we want uniform temperature throughout. So if you are putting rib here, this zone there is no flow. You can say there is only vortex generated in with air generation with air in this part. So that part that is not good. So that's why if you put little bit inclination, that is good. It will enhance the efficiency. Impact of rib cross sections. Rib cross section, as I told you earlier, there was a rectangular type or square type, and circular and triangular. There are three things here shown. You may consider the different shapes. So if you use this sharp corners like here, you can see this is the sharp corners in the case of square. So what happens here? If you are using sharp corners, this separation will start early. Okay, so separation will start early, then reattachment also will be early here. Here, reattachment. But if you are using this side, if you go circular means this is streamlined flow. You can say in the circular. So this separation gets delayed, and it will take slightly. This distance is larger distance you can say than this. So this way, this is not good actually. We don't want this unnecessary part, this part. We want a reattachment should occur as early as possible. Okay, so reattachment we want. So this part is good if you use this type of sharp corners you can say. This is in between. This will give you in between type of things. So summary of this experimental research gap, just talking about the research going on. So experimental studies on the performance of SH with various types of artificial roughness has been extensively carried out. So many people have done this experimental studies on this artificial roughness. And little bit you can say more variation if you want to do, you can do easily in the CFD analysis. Okay, so CFD analysis with the more variations you can say of any cross sections, you can vary different. You can put there, you can do easily that. So if you see that the paper, research paper initially started long back 1970, 80 papers or so, you will find experimental papers are many. So CFD actually part because the requirement of workstations, high performing computers, this thing started late. So you will find little bit less paper than means in this area on CFD, using CFD. So in that, even though extensive research has been carried out on the secondary generating flow employing artificial roughness in rectangular duct SH, the strength of secondary flow in various other duct cross sections and the effect of ribs in their thermohydraulic performance have not been explored in detail. Duct cross section, mainly if you see most of the papers are based on the rectangular duct section cross sections. Other cross sections like triangular or some modification in the walls, okay, semicircular type, that is not there. It's very limited. So in this, we'll talk about the numerical and experimental part. Both will talk. So numerical part, this is a computational how we did here. Safety analysis, we used ANSYS Fluent software for the safety analysis. Triangular duct SH with inclined ribs. This is, you can see the inclined ribs are like this in this way. Okay. So a triangular duct with inclined ribs. This inclination is varying from 30 degree to 75 degree. And we have varied the pitch, relative height, roughness, you can say relative height. So those things we have varied. Next, if you see this type of V ribs, okay, that was inclined earlier one. This is the V rib. In that you can see the C, figure C, you can see the beta angle, you can see with the flow direction. What is this angle beta? This beta we varied from 30 to 75 degree. Okay. You can see the pitch and roughness height we varied. This thing we kept 10 P by E is pitch, we kept 10 and roughness 0.05 height part. And this thing we published in Energy Journal. Okay. Another part is the side wall modification. If you modify a little bit, the earlier one, what is the widely used is rectangular. If you modify with semi-cylindrical side walls, little bit modification in the side walls, then this will give you some advantage. So this way we got some higher THPP, okay, thermohydraulic performance with a semi-cylindrical side walls. So in this also there is a baffle height, baffle pitch, those things we have considered, and angle, baffle angles. Okay. So W baffle, this is called W type. You can see it looks like W. Okay. V type we used there. Here W type we have used. Then in that W types there is a discrete inclined baffles here. Discrete means for the secondary flow to pass here, we have put some holes. You can see cut sections. You can see here cut. And that cut we have put like leading edge. This is the leading edge. You can say here. So these two cut is here. Okay, this is, you can see. Here it is trailing apex. So leading apex here, and this is trailing apex. Trailing apex here. This we have put the gap. And the third one is gap at the leading and trailing apices. So this way, both places we have put gap. Then we have seen the effect on that performance. This is the meshing we have meshing we generated. So meshing part you can see this is the triangular duct meshing, and this one is the semi-cylindrical SH with semi-cylindrical sidewalls and with baffles. See, whatever if you do the meshing, these are the basic part. You should do the grid independence analysis. Grid independence study is very important if you do the safety analysis. Whether your the results should not depend on your grid size. Okay, so if you are varying the grid size, your results should not vary. So that point you should do the study. So you can see here if it is coarse grid if you are using, this is the result. And as you are refining it, okay, going like this, then at this point you can see here the variation is less. This side, almost the gradient you can see, the difference you can see. It is becoming flat here. So this side you can consider the number of grid is the optimum grid 3.6. Even if you go to 4.8, it won't vary much. But this side you can see that there is a difference. So after this, if you refine even, it will not depend on the grid. it will give the same result. Like this, if you come to the Nusselt number here, the second one for this is semi-cylindrical sidewalls. First one was triangular. Here also you can see if you take the coarse grid, it's 1 lakh here, 1 million, 10 lakh. So here if you see this 1 lakh to 2 lakh, it is varying. So if you go to this side, then you are getting almost flat. There's a change is negligible. So that you can consider, and then you do the study. So this is the grid independence study. So after the number of grids, like here you can say 2 million, there is no change, so that you can consider the optimum grid. Different bonding conditions, what you can use: duct inlet, absorber plate, what is the heat flux you are giving, what is the pressure, what is the adiabatic walls. So these side walls and bottom walls are considered adiabatic, and these are the heat flux and these things. We have calculated, we have used different models also, and compared with these models, which one is giving better results. So first one is details water correlation, you know that. RNG capsule model, K omega SST model, Reynolds stress model. These things we have used. Okay. Another one you can see this for the friction factor also similar way, Blassius correlation, RNG capsule, K omega SST, Reynolds. So these models we have used, and you can see this correlation always giving the higher side. This one, cell number here, even the friction factor also, but not much, very much different. You can say. So RNG capsule is just close to that. Here also RNG capsule is close to that. So others also in the Nusselt number case, if you see, not much variation is there. Friction factor there is a little bit variation. RNG capsule is giving close to that Blassius correlation. Now the data reduction, if you say that Reynolds number, they are the very basic part. Reynolds number, OVT value, heat transfer coefficient, how you calculate. See, the thing is, people do mistake here in calculating the heat transfer coefficient. It is not that who are new in this, you should not do that mistake. Actually, the H, what you are finding here, this heat Q you are giving here, means Q is how much heat flux you are supplying on that. Heat flux, actually that is Q is the heat flux here. Q is HA delta T, so Q is heat flux. That second one, heat transfer coefficient, divided by TP. P is the plate temperature, and B is the bulk mean temperature of the air or fluid. So this way you should calculate H. You should not calculate using RE. Suppose you have some RE is there, Prandtl number is there, and putting some correlation in Dietz-Walter and getting a Nusselt number, and with that Nusselt number you are getting H. That is not the correct way. If you want to calculate, then this safety analysis why you need is. So this is the correct way. You should calculate you can take the mass weighted average of the or area weighted average of this plate temperature. Then bulk mean temperature, you can get that mass weighted average or volume weighted average. Slightly difference will be there. Mass weighted is better. This you can calculate. Then you get this H, transfer coefficient. Okay, this important part were the new researchers for them. Once you got the H, then you calculate the Nusselt number, Dy. Okay, come down. H by K, whatever. So friction factor, this correlation you can use, and thermohydraulic performance parameter. That this one I was talking. If you are increasing that, putting more turbulators in that, fins you are putting more, then you are resisting the flow. So what will happen? Your pressure drop will increase. Okay, so one side your pressure drop will increase. another side your Nusselt number will increase. Okay. So the thing is, you can see the pressure drop is the negative part. Okay. And second, you don't want pressure drop, otherwise your pump, your fan power will increase. You want more friction, you want more heat transfer. So Nusselt number should be more. So this ratio you can see here, Nusselt number. Okay, if your rough, NUR means the roughness surface. What you are putting after that means you are putting fins, that is called roughened surface. And that's a NU, normal NU is the for a smooth surface. So this ratio you have to see that if it is smooth, what is NU? If it is rough, what is NU? This is the ratio, will be the numerator side, and denominator side, that friction factor. So how the friction factor is increasing, but friction factor ratio is not taken as the just ratio only. This is the power is 1/3. So friction, how much you are increasing, that power is 1/3, means this is given less importance than the Nusselt number. So this derivation is also there, you will find wave and Eckert, right? So this derivation is a different. Actually, this will be different for the different cases also. Cases meant to say if there is a more pressure drop difference, pressure drop or pumping power difference is more, then you cannot use this equation. If pumping power is different, if you are comparing two different fluids, okay, one has very high viscosity, one has less viscosity, you cannot use this relation. There are different relations for that PHPP. Okay, in that you may be requiring, in place of Nusselt number, you may need to put that heat transfer coefficient. And here, in the case of friction factor, you may need to put here pumping power, ratio of pumping power, where there ratio of heat transfer coefficient. That is the thing. If you have more difference in pumping power, coefficient of performance, how much you are getting the heat utilized, you are able to utilize the heat, and divided by the pumping power of the fan. Here thermal efficiency, utilized heat divided by the supplied heat. Supplied heat means this is the solar radiation part. I is the solar radiation into area of the collector plate. Collector efficiency, this pumping power part is only removed. Okay. Net exergy flow, this is the exergy flow part. How much exergy and exergy inflow and exergetic efficiency. Okay. So exergetic efficiency always will be less here, because the thing is we consider that radiation is coming from the sun, that heat is coming from the sun, and sun temperature is very high, at around 5800 Kelvin. Okay, 5800 Kelvin, in that range. So sun temperature, as you take here, this efficiency will be very, means exergy inflow, this will be, you can say, the will be more, you can say. If you are taking this more and utilized part is this part, you can see the exergetic efficiency, ES will be more, then what will happen to this? Efficiency will be very small. Very good. Okay, let us see the experimental setup part also. This is the methodology I'm talking, the result discussion we'll talk later. So experimental setup, how you can see this reefs and all. Okay. This type of things. W reefs here. Okay. This is the layout of the experimental setup. So it's done here. Here you can, the thing is, when you do the experiments, you should be careful about the, even in the safety analysis also, inlet section, then experimental section, test section you can say, and the exit section. This dimension is very important. You should use some standard. Okay. So that standard is very important. How much distance it should be there, inlet part, then this test section and exit part. Okay. Otherwise, based on this also paper will get rejected. The important part. If you are not maintaining the proper distance as per the standard, you may get the higher THPP also. You are not maintaining. Now the validation part. Earlier part, what I showed you that grid independence analysis, those things. Now the validation part, you can see the present study and some experimental studies. We have validated our numerical methodology. Actually, we are validating, because what we are going to do the same thing you will not get in the paper, or sometimes if it is there, experimental is there and numerical is not there, then you can do that study. Most of the time you will find that both things are there. So your study will be different. So that you, when you are validating, you should take the same conditions what is there in the paper that you validate, then you change your condition so that the methodology will be same, but conditions will be different. So that way you can do the validation. You can see here Nusselt number part is your Reynolds number increases here. Then Nusselt number here, black line, you can see black line is increasing. Okay. This is common for the smooth pipe also and rough pipe also, rough channel also, in that. And as Reynolds number increases, your friction factor also it decreases. This is a very common thing for both the things. So that in the case, if you have a rough surface and if you have a smooth surface, what is the change that matters actually? Okay, in both the cases, you can see that the trend is same, but how much change is there, that matters. Based on that, THPP you will get. Here also, in the case of semi-cylindrical sidewalls, you can see Nusselt number is increasing and friction factor is decreasing with increase in Reynolds number. Okay. So the thing is, this validation, you can see the error. Error we should not say, we should say the differences. The differences we are getting, deviations we are getting around, only the maximum is 10%, you can see in the case of friction factor. Nusselt number 7%. Here the second case, semi-cylindrical sidewalls also 9%, 10% in that range also. Okay, so if it is the range is in this 10% range, then you can accept it. Sometimes even more also you will get. CFD to experiment, there will be deviation around 20% also, some cases. So this paper was published in Renewable Energy. Let us see the results part, results and discussion part. So these three different aspects we will talk. So results and discussion part about triangular duct with V-ribs. You can see here, if you change this inclination, here this one is the triangular duct with V-ribs. In that inclination of V-ribs, you can see inclination is changing. Here is a different, angle is different. First one is 60 degree, then 45 degree, then 30 degree. Inclination is changing like this, you can see. So if you change the inclination, you can see the Nusselt number, how it is varying. Nusselt number in this case, in the first case, it is higher. Slightly means less, in between is going higher here, then again decreasing. So 30 degree, it is this one. Then 45 degrees here, like this, 60, like that we have done. So what is happening basically here, you can see. If you are making it 90 degrees almost flat, you can say, okay, with that. So if it is not inclined, what happens? There is no secondary flow, you can say, if there is no inclination in that. This 90 degree I'm talking about. So there is no secondary flow. With actually with secondary flow, we are getting higher this side, you can see. So not only this thing, you can see almost as you go the lower side, you are getting higher. But another part is also there here. What is happening with the friction factor? Friction factor also, you can see this. There is a variation is different like this. It's coming. So the optimized is what? Optimized is the THPP. what THPP you are going to get. You may get sometimes, okay, Nusselt number is always increasing. It's good. But friction factor, what is happening, that also you have to see. And that ratio, what the THPP is there, that you have to find and see that how much increasing. If it is keep on increasing THPP, then you go on that varying that parameter and increase THPP as much possible. But it won't happen that in that way. So in this, you can see the temperature contours, turbulent kinetic energy contours. Okay. So how it is, if you see that turbulent kinetic, this temperature contours, you can see. This is the first one is the smooth plate. The smooth plate, if it is this plate, the top one is the absorber plate actually. Absorber plate temperature is higher. Higher temperature means what? Higher temperature is not good actually. Absorber plate temperature is high means you are not able to remove heat from that surface. And due to that, what will happen? The losses also will increase from the absorber plate to the top side losses. That will increase. So always we should try to make it uniform, this temperature. Temperature should not be higher. So that's why you can see the higher here. Then second case is ribs put little here. The third one is the different way, that merging, this way. No, second one also, transverse rib only, 90 degree, this one. This is the inclined ribs. Here, what is happening, you can see the temperature is less in this top surface temperature, you can see is not that much high. Here, but the center one is high. Center one is why it is happening higher, because the merging of secondary flows from both sides is coming, V ribs type, and merging at the center, you can see. Due to that, there is a increase in temperature at the center. Here you can put discrete something, you can make hole, something cut section you can put, then there won't be this much increase in temperature. Or don't make it here, you can make two discrete, this side, cuts part of in that. Okay, so with that you can decrease that. So these are the things, these are the effect of putting the fins in that. Okay. If you see the THPP part here, thermohydraulic performance parameter, how it is happening. Now you can see the angle here. Beta 90 degrees is the lowest one here, you can see. Okay. Then beta 75 degrees increasing, beta 60 degrees here. Beta 45 degrees is the highest one. This one, 45 degrees. Beta 30 is below that. So you might be thinking that why we are not going beta 15 degree or this side. So 45 we are getting optimized, because the maybe that you are getting Nusselt number higher, but friction factor also you have to see. The ratio is the optimized one is beta 45 degree, highest you are getting. And above that, if you if you increase that beta or even the decrease the beta, you are not getting higher than that. Okay, both the cases. So you can see here that what we have seen, what we have got, the highest is 2.01 using this V rib. So this is the THPP what we have achieved. So there are different configuration. We are going to show you again in the next slide. So this is the one part. Okay, in that exergetic efficiency also we should show. Exergetic part, exergetic efficiency, how much we are getting here, around 2%, 2 to 2.4% or something in that range. And you can see this, the present study is slightly higher in that. You can see this. This is the exergetic efficiency what we are getting. This is the summary part, what I explained is a similar things is here. Nusselt number and friction factor values are substantially higher than the smooth absorber plate values. Both are higher. Okay. This is due to the separation of flow, reattachment, and secondary flow generation caused by the V-ribs. Thermohydraulic performance, we have seen the range. It is going up to the 2.01 maximum. Peak value 2.01 is obtained at beta 45 degree, and these are fixed things. And Reynolds number 7,500. Okay, so these are the things. Upon comparing this SH design with the triangular duct SH for similar input condition, the design exhibits superior performance. This design. Hence, for application requiring compact heat exchanger, especially at higher flow rates, a V-ribbed beta 45 degree triangular duct SH is a better choice. Okay, as I explained earlier. Now, this is that was V-ribs. Here, comparison of triangular duct and rectangular duct with inclined ribs. So, if you are putting inclined ribs, so let us compare with the rectangular duct and triangular duct, which is better. Okay. So, inclined ribs, if you are putting, and you can see here, this is secondary flow velocity. First graph. Contours of secondary flow velocity indicating the effect of duct cross section on the secondary flow development. So secondary flow, if there is a more, you'll get better enhancement. Okay, better performance. So you can see the here secondary flow part, that secondary velocity is more in this point here. Similar way, you can see the turbulent kinetic energy here. Turbulent kinetic energy is getting in all sides. Here, if you come to temperature side, more easily understandable part is the temperature part here. Temperature part, you can see this is the first one is smooth. The first one, this line is smooth. Second line is the ribs. But in initial, first one is that the Z is equal to 0. It's at the entry, you can say Z is equal to 0.4. Across the length, I am talking the axial length. Z is equal to 0.4 and Z is equal to 1 meter at the end, you can say. Different cross section second. So you can see one thing here is, first one, there is no rib. So it is smooth, almost you can see the variation is symmetrical, you can say here. Here variation is right side is temperature is more than the left side. That depends on the inclination of the rib. Actually, one side only one. This is not the V rib. This is normal inclined ribs only one. So one side it will go. The secondary flow will go to that side. So the temperature will increase on one side. It won't be symmetrical. So this is the effect here. You can see. So you can see these are the things here, and in this case, in the case of rectangular duct, also there are 3 sections. You can see the rectangular duct profile here. So both, if you compare and see this THPP, thermohydraulic performance parameter, actually in this it is slightly difficult to see that the temperature here also it is not that much, looks very high. But if you see the THPP part, actually the thing is why the efficiency is less. The another one main reason is the temperature should be uniform. Temperature should be less. Then heat loss will be less. So if you see this thermohydraulic performance parameter of triangular duct and rectangular duct. So triangular duct, you can see this is coming around 1.79 actually. This highest is 1.79 and this comes around 1.51. So this much difference is there. So this is around 1.79, 17% higher we are getting at 10,000 RE value. So these are the simple direct comparison you can do. We have done this with the rectangular and triangular. We are getting higher THPP in the case of triangular duct. Now we'll shift to the semi-cylindrical sidewalls. So you can see here solar air heater with semi-cylindrical sidewalls and W baffles. Baffles also we have changed. See the V, if you extend, then it will go to W. Okay. So different types of baffles you can use. So you can, people have earlier done some studies, but not with the different baffles. So you can, we have done some this validation part. So ducts with semi-cylindrical sidewalls enhance the secondary flow. This is Vidal et al. 2017, 2018. So impact of sidewall geometry on the thermohydraulic performance of SH. So sidewall geometry here, if you put the vertical geometry and if you put the this semicircular sidewalls, semi-cylindrical sidewalls. So you can see these two. Right side, you can see this second figure. You can see the comparison. The bottom one here is for rectangular and semi-cylindrical is the first one. You can see this comparison, these two. Okay. So this is the contours of transverse velocity, indicating the effect of sidewall shape on the secondary flow development. Primary flow is along x direction. So secondary flow development is more in, you can see secondary flow development. This red part actually that's showing the more velocity. You can see here. So this part, some part, actually the direct seeing this and comparing is, it looks a little bit not easy to do, almost looks similar here. Here, if you see the first one, first graph, you can see that Nusselt number and friction factor of the vertical sidewalls and this thing. Friction factor part, that red, you can see this friction factor part, you can see vertical sidewalls having more friction factor, you can see this, and semi-cylindrical sidewalls having less friction factor. It's same R, one R, if you compare this more friction factor you are getting. But Nusselt number, there is no change, almost negligible change. Both lines are, you can see, coinciding, this black line. So Nusselt number, there is no increase in heat transfer rate or heat transfer coefficient, but increase in, decrease in friction factor due to semi-cylindrical sidewalls. Because the sidewalls we have made smooth, so in that friction factor, due to the smoothness, that friction factor reduces. That matters actually. But let us see that. And we will see that Nusselt number, this secondary flow, if you see here how it is happening here in the secondary flow part. This is coming like this and going like this. This way actually this secondary flow is coming. You can see in this is the secondary flow like this from here. Variation you can see. This is the same region. There is no discrete here, discrete ribs. Discrete rib also in the next section will show you. So in this way, you can see that how the Nusselt number is changing, friction factor is changing. See the thing here, green line, you can see Nusselt number is highest. Friction factor also, you can see friction factor is highest in that same case. So now you have to optimize that. THPP you have to find. This way you cannot say that Nusselt number is also highest. That side our friction factor, what is the undesirable part, is also highest. Desirable part is the highest, undesirable part also highest. So how will compare? You have to compare with the THPP. And THPP, if you see, then you will find that thermohydraulic performance you can see here, and You can see here the present study is giving 2.27, and what we were seeing there, that you can see the PYD value based on that, this one PYD 0.92 and 0.092 is coming highest THPP. Okay, so here is what 0.92 PYD is the black one here, somewhere this one rectangular part, in between it is there, here also in between. So which one is in between, that is giving the better THPP, not the highest one, not the bottom one. Okay, so this is obvious also. So you can see this semi-cylindrical sidewalls is giving with the W levels 2.27. Other people have done this rectangular wall, rectangular duct with W levels also we have done. So we have achieved 2.27. So very high, you can see, compared to the 1.98 people and the other got. Okay, so this way, if you calculate now the thermal efficiency is very important for. Okay, so how much efficiency finally you are getting? So thermal efficiency, if you compare this, you are getting around 72% something in that range, 71, 72% efficiency. So this part is more important. Exergetic efficiency will not give you the direct significance, but thermal efficiency directly you can see that, okay, this much heat is coming from the solar rays and you are able to utilize 71% out of that. This comparison what I was showing you earlier with the photovoltaic cell, it was that efficiency is around 20% and here you are getting 70%. This much difference is there. So for the heating application, if you are using for heating application solar radiation you want to use, the better option is this direct thermal collector, not the photovoltaic cell. You cannot get in the photovoltaic cell, there is no chance of getting this much efficiency. Whatever the material you use, it is, I should not say whatever the material you use, in the future is possible. But till now, what the material we have, that UV part is there, that is contributing for the energy transfer, electricity. So UV part is very less in that. More part is IR part, infrared part, and visible rays part contributing more in this thermal part. IR part is the thermal part, actually, infrared. That is around 40-45% in that range. So 8 to 10% only we have UV, and then some visible part will contribute for that photovoltaic effect. IR part will not contribute. So this 45% is gone. So these are the problem in that. This is the summary of this. Rounding of the duct corners removes the smaller vortices near the corners and facilitates the smooth movement of cross flow across the sharp corners. What we are doing here, comparing with the rectangular duct with the semi-cylindrical sidewalls. Okay, so in this way, it increases the turbulent kinetic energy near the semi-cylindrical sidewalls, and friction factor will reduce in that. Thermohydraulic performance parameters we have reached with this WFLs 2.27. Okay, so this way different types of it was compared: W down reef, W up reef. Okay, W up reef, V baffle, this way. For the same exergy input, the SH design with semi-cylindrical sidewall performs better with an enhancement of this percent. Actually, this enhancement is not able to, it looks very high, 38%, 28%, but if you see this exergetic efficiency, I'm going to back this slide. Exergetic efficiency is around 2%. So increasing little bit here efficiency, that will come around 20-30% increment. Okay, suppose 2 to 2.5 is coming. So that is 2 to 2.5. It looks here to 0.5, but there it will be very high relative to that efficiency if you calculate change in efficiency. So that's why it shows like that 38%, 28%. from the base is small actually, 2%. Okay. This is solar air heater with semi-cylindrical side walls and multiple discrete inclined vessels. So discrete part we have used, as I told you earlier, we will, if you put some holes in that or some passage in that, then it will pass and the temperature will not increase at that merging point. The secondary flow is merging. So that this will talk on this. Just will take 2-3 minutes break. Okay. So we'll start from here. Then okay, I think 3 minutes break.
Hello, sir.
Just 2-3 minutes break we'll take. Some
Sir,
participants if you want to
Sir,
go.
time is 8 to 9:30. It is almost 9:30, sir.
Oh, time is over, huh?
Yes, sir.
You should tell.
Yes.
I thought it is half an hour is remaining.
No, sir. It's 9:30, sir.
Oh, see the things. I thought it is okay. Then we'll finish it. Okay.
Yes, sir. Yes, sir. We can.
Oh, sorry. I thought it is okay. This was over.
Yes.
Acha, ठीक है. We'll finish it better.
Yes.
Okay. So this part, solar air heater with semi-cylindrical sidewalls and multiple discrete inclined baffles. So discrete, if you are putting the inclined, inclined baffles were there. Now the only putting the multiple discrete in that. Discrete means passage we are creating in that. Then in that case, what is happening actually? If you see the THPP, THPP here is in that case. In that we have considered 3. A smooth plate you can see. First one, Nusselt number if you see. A smooth plate is very near to this. Then trailing gap at trailing apex, leading apex, okay, and leading and trailing apex. This type of things we have done. Then you are finding here Nusselt number is highest in the case of trailing apex if you are putting. Because the trailing side is the temperature is more. Their hole is needed. Friction factor, you can see that trailing apex, if you are putting that friction factor is also higher. So that overall, if you compare that, finally you are getting the gap at trailing apex only, you are getting highest. This is the experimental result what we have done. Highest we are getting in this. Okay, 3 around. So these are the things you can see the trailing apex. This is the leading side. Then this is the trailing side. Or this is next. So trailing part, this part, B part is the better. Okay, we are getting 2.69. Here you can see the collector efficiency around 70% is going, right? Here exergetic elevage will be 2-3% due to the sun temperature because we are calculating from sun temperature. If you take the reference temperature is different, then you will get higher. Coefficient of performance, we are getting around 4 in this. You can see this way. Okay, then this is the already explained the THPP we are getting very high here, 2.69. Okay, and efficiency also it is going around 70% higher collector efficiency. These are the conclusion, triangular and vertical. Already we talked about this. Okay. So now the better question answer sessions.
Yes, sir.
Participants can ask questions. Sorry, I thought it is in the, I saw timing, but
Yes, sir. You are too deeper in the explaining, sir. So almost 1.5 hours. Dear participants, if you have any queries or the questions, you can ask to us, sir. Then you can connect with us, sir. Later we'll provide you the details about sir. You can connect with the mail as well as you can have the collaboration with the for research also. I think no questions, sir.
ज़्यादा time ले लिया मैं. I'm sorry, actually I could not see
sir,
that.
actually this is the first day, so which started little bit later. so it will end by 9:30. It is too late actually. So
Okay.
I think
No,
so.
actually, this should little bit remind me. Actually, there is no screen here visible. Once I say it, and I could not see actually. My mistake also there. It's half an hour exceeded.
Yes, sir, definitely, sir. If again, uh,
Okay.
like we will add the further sessions also, sir. So
Mhm.
we can discuss it.
Okay.
Yes, sir. I think there is no questions from the participants, sir.
Okay. Okay. Thank you.
Sir, thank you very much, sir. So you have given the extensive information regarding the solar aerator, and also you have explained how the direct heating is better than the using the PV cells. So in terms of the efficiency and all. Also, you have explained the different types of air heaters and different artificial rib arrangement for the air heaters so that we can increase the efficiency. And you have explained this exergent energy analysis, which is very important in terms of the solar system to do the analysis, even if it is a CFD analysis or the experimental analysis. And also you explained this semi-cylindrical side walls. Even there are different types. So due to the even we extremely sorry that you got the little time, sir. So within this 1.5 hour, we have explained the very vast things to the participants. Definitely, all participants will take this knowledge and definitely they will go for the further research as well as the collaboration with you, sir. So if they get any questions, definitely, sir, we'll connect with you so that we can clarify the participants' queries, sir. Thank you very much, sir, once again.
Thank you.
You agreed for our request, sir, and you have delivered a very nice session, sir. Thank you very much.
Thank you. Thank you, Madhu.
Good night, sir.
Okay, good night.
Dear participants, we have shared the feedback link to the chat box as well as the WhatsApp, so which is opening to the maximum participants. So please check your end so that you can give the feedback for the second session also. Thank you all joining for this FDP for the first day sessions. All 2 sessions we successfully completed, and tomorrow we will join at 6 p.m. Thank you all. Good night.